Hi guys, welcome back to Sleep into Power. I'm NJ. Tonight, the language of the stars. How human beings, standing in the dark with no instruments and no maps, taught themselves to read the sky and used what they found there to plant their crops, cross their oceans, bury their kings, and explain their own existence. We'll travel a long way tonight. The first fires and the first stories. Egyptian priests waiting on a rooftop for one particular star. Babylonian scribes pressing eclipse records into wet clay. The Greeks, and a corroded lump of bronze pulled out of a shipwreck. Maya astronomers tracking Venus from a round tower. Polynesian navigators crossing thousands of miles of open ocean with nothing but the sky, the swell, and the birds. Norse sailors hunting for one steady star in a northern storm. The astrolabes of the Islamic world, and a man in Padua on a cold January night, lifting a small tube towards Jupiter and seeing something nobody had ever seen. Wherever you are tonight, and whatever hour it happens to be where you're lying, thank you for being here. And thank you to whoever suggested this one. You know who you are. I just want to share this with you quickly before we start. There's a Sleep into Power book on Amazon, in paperback and on Kindle. Everything here is on Spotify, for the nights you'd rather not have a screen anywhere near you. There's a second channel called Meditate into Power to help you relax and be still. And there's a Buy Me a Coffee page if you'd ever like to support the work. All of the links are down in the description. Thank you for watching as always, guys. Thanks for subscribing and for the likes. Tell me in the comments what you'd like to hear next, because that's where nearly every one of these comes from. And tell me where you are in the world and what time it is. That's everything. Let your head settle properly into the pillow. So let's begin. Now, the dark. Try for a moment to imagine a night that has never been interrupted. Not the night you know, not the night that glows faintly orange above a town, where the sky over a city is a kind of dirty amber, and the stars are a scattering of the very brightest, a dozen or so, holding on. Something else, something older, you are lying on your back on ground that is still giving up the last of the day's heat. There is grass beneath you, or sand, or the flat stone of a hillside, and it is warm against your shoulders, in a way that will fade over the next hour and be gone by the middle of the night. The air is cooling. You can feel it moving across your face, slow, unhurried, carrying the smell of dry earth and crushed vegetation, and somewhere behind you, wood smoke. There is a fire, a little way off. You can hear it rather than see it. The small collapses as a log settles. The occasional crack, sharp and startling, as a pocket of sap opens. The soft, continuous sound underneath, which is not really a sound at all, but a kind of breathing, and the light of it reaches you sideways, moving, so that the ground around you brightens and dims very slightly, over and over, without any pattern you could predict. Beyond that, insects, thousands of them, in the grass and the trees, making one continuous shimmering sound that rises and falls and never quite stops. Now and then something larger moves out there in the dark, and everything goes quiet for a few seconds, and then begins again. Somewhere, water. A river running low over stones, or a lake so still that when you walked past it earlier, you saw the whole sky lying in it, upside down and perfect, until an insect touched the surface, and the stars all shivered. Leaves are moving in a tree above you. Not much, just enough. And when you look up, the sky is not black. That is the first thing that surprises anyone who sees a genuinely dark sky for the first time. It is not black, and it is not empty, and it is not quiet. It is crowded. There are so many stars that the familiar shapes become difficult to find, because the patterns you learned are buried in thousands of fainter companions that you have never seen before. The gaps between the bright stars, which you always assumed were empty, turn out to be full, and behind those, further back, there is a kind of granular shimmer, a suggestion of more, going down and down past the point where your eye can separate one from another. Across the middle of all of it, from one horizon to the other, there is a river of light. The Milky Way, seen properly, is not a faint smudge. It is a broad band with structure in it. It has edges, and bright knots, and dark lanes running through it, like ink poured into milk. It is bright enough to be obvious the moment you step outside, and bright enough, on the very best nights, to cast a faint shadow. Almost nobody alive in the developed world has seen it like that. Roughly a third of humanity now lives under skies where it is never visible at all. Every single one of your ancestors saw it. Every night of their lives, unless it was cloudy. It was simply there, the way weather is there, the largest and most obvious thing in the world. Lie under it long enough, and something else happens. It moves, not quickly. If you stare, you will see nothing. But choose a star and line it up with the edge of a branch and look away and talk, and come back a few minutes later and it has gone. The whole enormous structure is turning, silently, all in one piece, wheeling around a single fixed point in the north. Watch through the whole night and the sky you saw at dusk will have swung right across and gone down in the west, and new constellations you did not see at the beginning will have climbed out of the eastern horizon while you slept. Watch across a year, and it turns out that the sky at midnight in the summer is a completely different sky from the one at midnight in winter. The same stars come back, always, in the same order, at the same time, and if you keep watching for long enough you begin to realize that the great slow wheel does not vary. Not once. Not ever. That is the beginning of everything. Because here is the situation a human being was in. For the overwhelming majority of the time our species has existed. You have no clock, you have no calendar, you have no map, and no writing, and no way of recording anything except by remembering it and telling somebody. And you have a set of problems that will kill you if you get them wrong. When will the rains come? When will the herds move? When should the seed go into the ground? How long until the cold? Where is the coast, if I cannot see the coast? Everything on the ground is unreliable. Rivers change course, forests burn. Landmarks are covered by snow, or by flood, or by the simple fact of night falling. The ground tells you where you are, only if you already know where you are. The sky is the one thing that never lies. It is the same for your grandmother as it is for you. The same in this valley as in the next one. The same when everything else has been taken away. It keeps perfect time, and it has been keeping it since before anybody was here to check. So people looked up, all of them, everywhere. That is what is genuinely astonishing about this story, and it is worth holding on to as we go, because you will hear it again and again tonight in different accents. Human beings in Egypt and China and Peru and the middle of the Pacific, separated by oceans and by thousands of years, with no contact of any kind, all did the same thing. They watched the sky. They found the patterns. They joined the dots into pictures. They gave the pictures names and hung stories on them, and used those stories to teach their children what to plant and when to sail. They built enormous structures out of stone that pointed at particular places on the horizon, on particular days. They worked out numbers so precise that when we recovered them, thousands of years later, we had to check our own figures. And they did it all with their eyes. No lenses. No instruments beyond sticks, string, shadow, and stone. Which raises the question we are going to spend the next few hours with. Is the sky a language? Because it behaves like one. It has units that repeat. It has grammar, in the sense that things happen in fixed order, and one event reliably predicts another. It carries information that can be extracted and acted upon. And it was read, independently, by dozens of separate civilizations who arrived at overlapping conclusions. But a language implies somebody speaking. And that is where this becomes something more than a story about calendars. Because almost nobody, in all those centuries, thought they were reading a physical mechanism. They thought they were reading intention. The sky was not a clock. It was a face, or a book, or a body, or an ancestor. And the regularity of it was not evidence of physics, but evidence of care. Getting from that to what we now believe took about 5,000 years, and it is one of the great journeys of the human mind, and almost every step of it was taken by somebody standing outside in the cold, at night, looking up, and paying attention for longer than was reasonable. Let the fire settle, let your breathing slow. We are going back to the beginning, before the calendars and before the temples, to the first time a human being looked at the sky and saw something in it other than light. Begin with darkness, because darkness is the thing that made all of it possible. For most of the history of our species, night was not a time. It was a place, and it was hostile, and you could not go into it. When the sun went down, the world simply closed. You could not see the ground under your feet. You could not see what was moving towards you through the grass. Your eyes, which are the instrument your entire body is built around, stopped working, and every advantage you had over everything else in the landscape went with them. The things that hunt do not have that problem. A leopard sees perfectly well at night. So the sensible response, for a long time, was to find something defensible, get inside it, and wait. Then somebody learned to keep fire, not to make it. Making it came much later. Keeping it, finding a burning branch after a lightning strike and understanding, and this is the extraordinary part, that this thing could be carried and fed and kept alive, and that it would go on giving out light and heat for as long as you looked after it. It is difficult to overstate what that did. Fire pushed the darkness back to a radius of a few meters, and inside that radius, the rules of the night were suspended. The predators would not come in. The cold was survivable. Food could be transformed, made softer and safer, and easier to get energy from. But the thing that mattered most was time. Before fire, the productive part of the day ended at dusk. After fire, it did not. There was now a stretch of several hours, every single night, in which a group of people sat together in a small circle of light, with nothing urgent to do. You cannot hunt in the dark. You cannot gather. You cannot work stone properly. Almost every practical task is impossible. So what happened in those hours? There is real research on this, and it is one of the more beautiful findings in anthropology. An American anthropologist named Polly Wiesner spent decades among the Juhohonsi of the Kalahari, and she recorded what people talked about by day and what they talked about by night, and the difference was stark. Daytime conversation was practical and often sharp. Who had done what? Land, resources, complaints, arrangements, jokes at somebody's expense. Nighttime conversation, around the fire, was almost entirely stories. Stories about people who were not present. Stories about the dead. Stories about places far away that most of the listeners would never go. Stories about spirits, and about animals that behaved like people, and about how things came to be the way they are. Firelight changes what human beings talk about. Something about the low, warm light, and the faces half in shadow, and the enclosed circle, and the fact that the world outside has gone dark and there is nowhere else to be, moves people from the practical to the imaginative. And above that circle, every night, for hour after hour, was the sky. Now consider the situation of somebody sitting in that circle, night after night, year after year, with excellent eyesight and enormous amounts of time, and absolutely nothing to distract them. They are going to notice everything. They will notice that some stars are brighter, that some are faintly colored, orange or blue or red, once you learn to look. That most of them hold their positions relative to each other with total fidelity, night after night, generation after generation, while a small handful of bright ones wander slowly through the others along a single road. That one region of the sky turns very slowly around a fixed point, so that some stars never set at all. And they are going to do the thing that human brains cannot help doing. They are going to see pictures. We are pattern-finding animals to a degree that is almost pathological. We see faces in electrical sockets and in the fronts of cars and in the burn marks on toast. It is not a flaw. It is an extremely useful bias, because in a dangerous world, the cost of seeing a predator that is not there is trivial, and the cost of missing one that is there is fatal. So we overread. We always have. Point that machinery at a random scatter of a few thousand lights, and it goes to work immediately. Which is why every human culture we know of made constellations, and why some of them are almost impossible not to see. Orion is the clearest case. 3 bright stars in a tight, evenly spaced, perfectly straight row, which is a configuration that essentially never occurs by chance, framed by 4 more bright stars in a rough rectangle. Everybody sees it. Everybody has always seen it. Cultures with no contact whatsoever have all grouped those same stars, and remarkably often they have seen a figure of a man, or a hunter, or a warrior. The Pleiades are the other one, a small tight knot of faint stars, clustered so closely that most people can count 6 with the naked eye, and a few can manage 7 or more. Almost universally, across the entire planet, that little cluster has been understood as a group of things, rather than as a single thing. A flock, a handful of seeds, a cluster of bees, and in a striking number of unconnected traditions, from Greece to Australia to North America, the Pleiades are a group of young women, usually being pursued by a man associated with the stars of Orion, who escape into the sky. Some researchers have suggested that this may be one of the oldest stories on Earth, carried out of Africa and preserved for tens of thousands of years. That claim is genuinely contested, and it should be treated as an intriguing hypothesis rather than an established fact, because stories can also arise independently, and the human imagination is not infinitely various. But the pattern itself is real, and it is very hard to look at without feeling something. Not every culture drew the same kind of picture, though, and this is the part that gets missed. In Australia, some Aboriginal traditions map the sky the other way round. Rather than joining the bright stars, they read the dark shapes between them, the lanes of interstellar dust that break up the Milky Way. Along the length of the galaxy, from the Southern Cross down towards Scorpius, there is a long dark form with a small head and a long neck and a wide body, and it is an emu. And the emu is not decorative. Its position through the year tells you where the emus on the ground are in their breeding cycle, and therefore when to look for their eggs. That is a functioning agricultural calendar, encoded as a shape made of nothing, held in oral tradition, in some cases for a very long time indeed. The Inca did something similar in the Andes, reading dark cloud constellations along the Milky Way as a llama, a fox, a toad, a serpent. 2 hemispheres, no contact, and both arrive at the idea that the darkness is also a picture. Somewhere in this long stretch, people also started counting. There are objects from the deep past that look, to a modern eye, like tallies. A baboon fibula found in the Lubombo Mountains between South Africa and Eswatini, roughly 43,000 years old, carries 29 clear notches. A bone from Ishango in Central Africa carries groups of marks in patterns that some researchers read as arithmetic. The obvious thought is that 29 is very close to the length of a lunar month, and a great deal has been written about whether these are lunar calendars. Be honest about what that evidence is. The marks are real. The dating is solid. What the marks were for is not known, and probably cannot be known, and interpretations range from calendars, to counting objects, to decoration, to something we have not thought of. What we can say is that human beings were making deliberate, repetitive, countable marks on bone tens of thousands of years ago, and that whatever they were counting, they had begun the habit of recording. The same caution applies to the cave paintings. There have been claims that certain groups of dots in the caves at Lascaux represent the Pleiades, and that other arrangements map the summer sky. Those readings are speculative and are not accepted by most specialists in Paleolithic art. What is not in dispute is that people crawled hundreds of meters underground by the light of animal fat lamps into total darkness and painted with immense skill for reasons that were plainly not decorative. They were doing something serious in the dark. We do not know exactly what. And running under all of it, there is the other thing the sky did, which had nothing to do with calendars at all. It gave people somewhere to put the dead. This may be the single most consistent idea in human culture. The sky is where the ancestors are. It is where you go. The lights are the campfires of those who went before, or the holes in the floor of a world above ours through which their light leaks down, or the souls themselves, fixed in place, watching. Ask why that idea occurred to everybody, and the answer is not mysterious. The sky is the only permanent thing. Everything on the earth decays, bodies decay, and quickly. Wood rots, stone weathers, people are forgotten within 3 generations. But the stars your grandfather pointed out to you are in exactly the same positions when you point them out to your grandchild, unchanged, undiminished, precisely where they were. If you are looking for a place where things do not end, there is only one candidate, and it is directly overhead every night of your life. So the sky became the first religion, more or less everywhere. Not because anyone reasoned their way to it, but because it was the obvious location for permanence in a world that offered none anywhere else. The gods lived up there, the dead went up there. The order of the heavens became the model for the order that a king was supposed to impose on the earth. And a ruler who could predict what the sky would do next was demonstrating something more persuasive than an army. And that, in the end, is why the astronomy came. Not from curiosity, at least not at first. People watched the sky that closely because they believed something was being said, and they wanted to understand it, and they thought their lives depended on getting it right. They were correct about the last part. They were just wrong about the reason. The fire has burned down to a low red heap now. Somebody reaches over and puts another branch on, and for a moment, the sparks go up in a spiral, climbing, and from where you are lying, they rise into the field of stars, and it is briefly impossible to tell where the sparks end and the sky begins. Everything changes when people begin to farm. A hunter who reads the season slightly wrong loses a few days. A farmer who reads it wrong loses the year, and everything that depended on the year, and possibly the village. Put the seed in too early, and a late frost takes it. Too late and the crop does not ripen before the cold, or the rains come and rot it in the field. The window is often only a couple of weeks wide, and it arrives once. And if you miss it, you wait 12 months with whatever you have left in the store. So the question that presses on the first farming societies is not philosophical at all. It is brutally practical. How do you know what day it is when the days all look the same? You cannot use the weather. Weather is the least reliable thing there is. A warm spell in February will fool you completely, and a cold snap in May will fool you the other way. Every farmer in history has been fooled by both. You cannot count the days, not reliably, not without writing, not over years. The moon is the obvious first answer, because it is impossible to miss. It goes through its cycle in the sky, in front of everybody, over and over, a thin curve in the west after sunset, thickening each night, riding higher. Then the full moon, rising as the sun sets, lighting the whole landscape well enough to walk by and to work by. Then the slow thinning on the other side, rising later and later, until it is a fine sliver in the east before dawn, and then nothing at all for a night or two, and then it begins again. 29.5 days, Near enough. You can count it on your fingers if you have enough of them, and you can mark it on a stick or a bone, and you can teach a child to recognize every stage of it in a single season. Almost every early calendar in the world is a moon calendar. It is why we say month, which is the same word as moon, and it does not work. That is the problem that sits underneath thousands of years of astronomy in every civilization on Earth, and it is worth understanding clearly, because it is the engine that drove an enormous amount of what follows. 12 lunar months come to about 354 days. The solar year, the time it takes for the seasons to come back round, is a little over 365. The gap is 11 days, which means that if you run a pure lunar calendar, your months drift. The month in which you always planted barley happens 11 days earlier against the seasons every year. Within 3 years, you are a month out. Within 16 years, your midsummer festival is happening in the spring, and within 33 years, it has gone all the way round and come back. There is no way to fix it with arithmetic alone, because the two cycles do not divide into each other. They are, in the most literal sense, incommensurable. The universe simply did not arrange the moon and the sun to agree, and every calendar in human history has been a negotiated settlement with that fact. Some cultures gave up on the moon and went solar. Some kept the moon for religion and ran a separate solar reckoning for farming. Most of them did the messy, practical thing, which is to add an extra month every few years when things had drifted too far, a process called intercalation, usually decided by a priest, usually late, usually arbitrarily. And to intercalate sensibly, somebody has to be able to tell, independently of the calendar, where the sun actually is in its year, which brings us to the horizon. Here is the observation that unlocks it, and it is available to anybody willing to stand in the same spot for a year. The sun does not rise in the same place every day. Watch from a fixed position, with a distant hill or a tree line to measure against, and through the winter you will see the sunrise creeping north along the horizon, a little further each morning. It speeds up through the spring, slows again through early summer, and then, around midsummer, it stops. For several days it rises in essentially the same place. Then it turns and starts back the other way. The word solstice means, more or less, the standing still of the sun. 6 months later, at the other end, it does the same thing at its southern extreme. And between the two turning points, twice a year, it passes through the midpoint, where day and night are of equal length. 4 fixed, unmistakable, unfakeable events in every year. They cannot drift, they cannot be argued with, and they can be observed with no equipment whatsoever, provided you have somewhere reliable to stand and something on the horizon to line up against. So people built the something. This is the point at which astronomy starts leaving physical traces you can still walk into, and there are a great many of them, on nearly every continent. At Newgrange in the Valley of the Boyne in Ireland, there is a great mound of earth and stone, built around 5,200 years ago, older than Stonehenge and older than the pyramids at Giza. A single narrow passage runs 19 meters into it, roofed with enormous slabs, and at the end there is a chamber. Above the entrance, deliberately built, there is a rectangular opening called the roof box. For most of the year it does nothing. For a few mornings around the winter solstice, if the sky is clear, the rising sun comes over the ridge on the far side of the valley, and its light enters that box, travels the whole length of the passage, and lands on the floor of the chamber at the center of the mound. It lasts about 17 minutes. Then it goes. They built a structure with hundreds of thousands of tons of material, moving stones over many miles, over what was probably decades, so that on the darkest morning of the year, a single beam of light would enter the deepest and most sealed space they had, and touch the floor, and leave. Nobody knows what they believed about it. There is no writing. What we can say is that these were farming people who understood their sky precisely enough to build for it. and who thought the return of the light at the year's lowest point was worth that much labor. At Stonehenge on the chalk of southern England, over centuries of building and rebuilding, the great axis of the monument was laid out along the line of the midsummer sunrise in one direction and the midwinter sunset in the other. Stand in the center on the right day, and the sun does exactly what the architecture says it should. Out in the western desert of Egypt, at a place called Nabta Playa, there is a small stone circle set up by cattle herders around 7,000 years ago, well before dynastic Egypt existed. Several of its stones appear to line up with the summer solstice sunrise, which in that region announced the arrival of the seasonal rains, which was a matter of life and death for people who depended on the seasonal lake beside it. In Germany at Goseck, there is a circular enclosure of ditches and wooden palisades built around 6,900 years ago, with gates that frame the winter solstice sunrise and sunset. And on a dry ridge on the coast of Peru, at Chanquillo, 13 stone towers stand in a line along the crest of a hill, evenly spaced, like the teeth of a comb. From 2 observing points, one on either side, the towers mark out the sun's entire annual journey along the horizon. The sun rises or sets in a slightly different gap between the towers every few days. That is a calendar you can read to within a day or two, from the ground, with no training. It is around 2,300 years old, and it is the earliest solar observatory of that kind known anywhere in the Americas. Consider what these places have in common. They are enormous. They took generations. They involved organizing labor on a scale that implies real social power. And they were built by people who could not write, in different millennia, on different continents, with no possibility of contact. What every one of them is doing is the same thing, fixing a line between a place on the ground and a place on the horizon, so that a moment in the year can be caught and held and repeated for as long as the stones stand. They are machines for knowing when, and once you can reliably say when, an enormous amount follows. You can plant at the right moment every year without guessing. You can tell people across a whole territory to gather on a particular day, and they will arrive, because the day is defined by something everybody can see. You can predict, out loud, in front of a crowd, that the light will come back, and then be right. That last one is not a small thing. A society that can promise the return of the sun in the depth of winter, and deliver, has something worth more than grain. The moon is up now, a little past half, riding in the south. It is bright enough to have washed out the fainter stars around it, and bright enough to lay a pale grey light across the whole landscape, so that the grass has color of a sort, and the trees have edges, and there are shadows on the ground, soft ones, from a light that is not warm at all. By the time it sets, the sky will have turned again, and the eastern horizon will be beginning to think about morning. Move now to a flat roof on the east bank of a river, in the last hour before dawn, in the middle of what we would call July. The heat has not gone. It never entirely goes here in the summer. The mud brick under your feet is still giving back the temperature of yesterday, and the air is thick and completely still, and there is a smell of river mud and dust and the ash of last night's cooking fire. Below and around you, the town is asleep. A dog somewhere. The creak of a boat's rope down at the water. The river itself is low, shockingly low, if you have only seen it in flood. Sandbanks stand out of it, pale in the starlight, and the channel has shrunk back, and the fields on either side are cracked and grey and dead. Nothing has grown for weeks. The last of the grain is in the store, and everyone is counting it. This is the worst part of the Egyptian year, and everybody on that roof knows it. And the man standing beside you has been coming up here every morning for 19 days. He is a priest, and his job tonight is to watch one particular part of the eastern horizon. The sky over there is beginning to soften, not light yet, but no longer black. The faintest thinning, low down, where the stars are starting to lose their edges. And then, just above the horizon, In the gap of a few minutes before the growing dawn drowns it out altogether, a single star comes up. It is very bright, brighter than anything else in the sky, and low down through that much atmosphere, it does not shine steadily. It flares and flickers and changes color, throwing off flashes of white and blue and red, sitting there on the edge of the world for a few minutes, and then dissolving into the morning. That is Sirius. The Egyptians called it Sopdet, and it has not been visible at all for about 70 days. Here is the mechanism, and it is the single most important idea in ancient astronomy, so it is worth taking slowly. Every star, over the course of a year, spends a period hidden. This is not because anything happens to the star. It is because the sun, moving steadily along its annual path through the background stars, eventually arrives in that part of the sky, and while it is there, the star is above the horizon only in daylight and cannot be seen. Then the sun moves on. And there comes one particular morning when the star has pulled just far enough ahead of the sun to be glimpsed, briefly, low in the east, just before sunrise, for the first time in months. That morning is called the heliacal rising, and it happens on the same date every year. It is the most precise natural clock available to the ancient world. Not approximate, precise, to within a day or two, forever, requiring nothing but a clear eastern horizon and the patience to get up early for a fortnight. And for Egypt, the heliacal rising of Sirius came at almost exactly the moment the Nile began to rise. Consider what that meant to the people on that roof. The flood was everything. Every summer, monsoon rain falling in the Ethiopian highlands 1,000 miles to the south, on mountains no Egyptian had ever seen, swelled the river until it came over its banks and spread across the whole valley floor. It stayed for weeks. When it withdrew, it left behind a layer of black silt, fresh and rich. And that silt was the reason a strip of desert a few miles wide was one of the most productive agricultural regions on Earth for 3,000 years. They called their country the Black Land, after that mud. A good flood meant a full year. A weak flood meant hunger. A flood that failed several years running meant the collapse of the state. And it happened, and there are texts describing it. And nobody in Egypt knew where the water came from. The cause was completely invisible to them, occurring in a country they had no contact with, produced by weather they had never experienced. What they had instead was a star that appeared over the horizon at the right moment, every single year, without fail. You can see how this looks from the roof. You have no way of knowing about Ethiopian monsoons. What you have is a bright star that vanishes for 70 days, returns on one specific morning, and is followed within days by the water rising. Year after year after year, for as long as anyone has kept records. That is not a correlation. That is, to any reasonable person standing on that roof, an announcement. So Sopdet was a goddess, identified with Isis, and her return was the beginning of the year, and the great temple calendars were built around her. Egypt also did something else, which was quietly revolutionary. They ran a civil calendar of 365 days, made of 12 months of 30 days each, plus 5 extra days added at the end. Clean, regular, easy to administer, with no lunar messiness in it at all. 12 tidy months for taxation and record keeping and the running of a state. It was one of the first genuinely solar calendars in the world, and versions of its structure eventually reached us through Rome. But it had a flaw they knew about and did not fix. The actual year is about 365 and a quarter days. Without a leap day, the calendar loses a day every 4 years against the real seasons. So the Egyptian civil year slid. Slowly, relentlessly, a day every 4 years. A month every 120. Over the centuries, the month called the month of inundation drifted right around into the winter and then into the spring, and eventually, after about 1,460 years, arrived back where it started. They must have known they had the star to check against. They kept two systems running side by side, the drifting civil calendar for administration and the star for the real agricultural year, and they simply lived with the mismatch for millennia, which is a level of tolerance for bureaucratic imperfection that any modern government would recognize. Now, the night sky itself, as an Egyptian saw it. Look north. There is a region up there that never sets. The stars close to the celestial pole simply wheel round and never touch the horizon, never disappear, never die. The Egyptians called them the imperishable stars, and they meant it literally. Everything else in creation set and rose again, which is to say died and was reborn, which was the central drama of their religion. Those stars alone never went down at all. That was the destination the dead king was aiming for. The texts inside the pyramids speak of him ascending to join them, becoming one of them, entering the company of the things that do not end. Look south, in the winter, and there is Orion, rising over the desert. The Egyptians called that constellation Sahu, and they associated it with Osiris, the god who was killed and dismembered and put back together, and became lord of the dead. Sirius, following behind it, was Isis, his wife, who did the putting back together. So the two brightest things in the winter sky were a husband and a wife. And the story of their separation and reunion was the story every Egyptian expected to live out after death. They divided the sky into 36 groups of stars called decans, spaced round the ecliptic, each rising about 10 days apart. As one decan rose, another was setting, and by counting which decans crossed the sky through the night, priests could tell the hours in darkness. Diagrams of these appear painted on the insides of coffin lids, so that the dead would know what time it was. That is where our 24-hour day comes from, filtered through several later cultures. 12 divisions of the night, taken from the decans, matched by 12 of the day. And then there is the alignment of the pyramids, which is a genuine mystery and deserves to be handled carefully, because a great deal of nonsense has been attached to it. Here is what is actually true, and it is remarkable enough. The Great Pyramid at Giza is aligned to true north, with an error of about 3/60ths of a degree. Not magnetic north, which wanders. True north. That is an extraordinary piece of surveying for a structure covering 13 acres, built 4,500 years ago, by people with no compass, no telescope, and no written mathematics of the kind we would recognize. How they did it is not settled, but the best explanations all involve stars. One well-regarded proposal is that they watched two particular stars on opposite sides of the pole and marked the moment when one was directly above the other, since the line between them at that instant passes through true north. Another involves bisecting the rising and setting points of a single star. Both would work. Both require patient night observation and careful marking with the simple tools we know they had, a sighting instrument called a merket, and a slotted palm rib for taking a line. What is not established, and what you will hear repeated constantly, is that the 3 pyramids at Giza were laid out to mirror the 3 stars of Orion's belt. That idea was popularized in the 1990s, and it is a fringe position in Egyptology. The alignment is approximate rather than exact. The 3rd pyramid appears to have been planned differently from the first 2, and no Egyptian text anywhere describes such an intention. Egyptologists who have looked at it closely think the layout is better explained by the geology of the plateau and the practicalities of construction, none of which means the Egyptians were not stellar, they plainly were. It simply means that the specific claim is not supported, and that the real astronomy is more interesting than the invented kind, because the real astronomy is in the temples. At Karnak, the great axis of the Temple of Amun is oriented so that at midwinter the sun rises in line with it, and the light travels down the length of the sanctuary. At Abu Simbel, far to the south, the temple was cut into a cliff, so that on 2 days of the year, the rising sun reaches down a corridor 60 meters deep and lights the statues in the innermost chamber. Think about what it took to build that. The chamber is inside solid rock. You cannot correct your aim once you have started digging. The alignment has to be established before the first chisel goes in, and then held, for years, through the whole excavation, in the dark, underground. They got it right. The sky is fully light on the roof now, and the star has gone. The priest is already going down the stair to carry the news, and within the hour the temple will know, and within the day, the river towns will know, and along 1,000 miles of valley people will begin getting ready for the water. Out in the fields, the cracked mud is still grey and dead. It has perhaps 5 days left. 600 miles to the northeast, between 2 other rivers, the sky was being written down. The land is flat here, in a way that Egypt is not. Enormous, level, alluvial plain, stretching further than the eye can follow in every direction, broken only by date palms along the irrigation channels and by the artificial hills that people have built. The air smells of river water and reeds and animal dung, and the particular dusty smell of sun-baked mud brick, which is what everything here is made of, because there is no stone. No stone at all worth speaking of. Every wall, every temple, every house in the greatest cities of the ancient Near East is made of river mud, shaped, dried, stacked, and slowly returning to river mud again. Which is why the ruins are hills rather than columns, and why the tallest thing for 100 miles is a stepped tower rising in terraces above the roofs of the city, with a stair up the front of it, and a small shrine at the top. And on that flat plain, with those enormous unobstructed horizons, and a climate that gives you clear nights for much of the year, people watched the sky more systematically, over a longer continuous period, than anyone else in the ancient world. They also had something no other early civilization had to the same degree. They had a filing system, because the same mud that made the buildings made the tablets. You take a lump of clay, work it into a pillow shape, press marks into it with the cut end of a reed while it is soft, and let it dry. If you want it to last, you bake it. Baked clay is close to immortal. It does not burn, which means that when a palace was destroyed by fire, as they regularly were, the fire baked the archive and preserved it. It does not rot. It does not fade. It survives being buried for 3,000 years and comes out legible. Papyrus decays. Parchment decays. Paper decays. Clay just sits there. So we have hundreds of thousands of these tablets, and among them are the longest continuous run of astronomical observations that any civilization has ever produced. In some cases, the record is unbroken for 7 centuries. Now, why were they doing it? Not for farming. They had the seasons sorted well enough. Not for navigation. They were not a seafaring people in any serious way. They were doing it because they believed the sky was a message, and that the message was about the king. This is the world of celestial omens, and to understand it you have to set aside any sense of it as primitive. It was rigorous, it was systematic, it was practiced by trained professionals with a complex reference literature, and it was, in its own terms, empirical. The reasoning went like this: the gods control events. The gods are associated with the heavenly bodies. Therefore, what happens in the sky is a signal about what the gods intend to do on the ground. If you can catalogue which celestial events preceded which earthly events, you can build a lookup table, and thereafter, when you see the sign, you know what is coming. So they built the table. There is a great series of tablets called Enuma Anu Enlil, running to about 70 tablets and something like 7,000 omens, and it is exactly that. If the moon is eclipsed in this month, on this day, in this watch of the night, then this will happen. If a halo surrounds the moon and a particular planet stands within it, then this. If Venus appears in the east on this date, then rain or drought or the fall of a certain city. It is enormous, and it is organized, and it is the direct ancestor of astrology. But here is the thing that makes it matter, and it is one of the quiet turning points in the history of thought. If you want to check the omens, you have to observe. Constantly, accurately, and forever. Because you never know which observation will turn out to be significant. So the Babylonian state paid people to stand on the ziggurats and the palace roofs every single night and write down everything. We have their reports. They were sent to the king, and they read like the work of professionals. This month the moon and the sun were seen together on the 14th day. The planet Jupiter was in front of such and such a star. There was a halo. It was cloudy and I did not observe. That last one is important actually. They recorded when they could not see. That is the mark of somebody keeping a genuine record rather than telling a story. They also recorded, alongside the sky, the price of barley and wool and dates, the level of the river, and the weather. The astronomical diaries are among the most valuable economic documents from the ancient world, because somebody wanted to correlate everything with everything. And then, after a few centuries of this, something began to emerge from the data that nobody had predicted: patterns. The clearest one concerns eclipses, which mattered enormously because a lunar eclipse was the most alarming omen there was, and was understood as a direct threat to the life of the king. Eclipses look random. They arrive without warning. The moon turns the color of dried blood in the middle of the night, and there is nothing whatever you can do about it. But if you have 300 years of records, and you go through them looking for structure, you find that eclipses repeat. After an interval of about 18 years and 11 days, a very similar eclipse occurs again, in a similar configuration. That interval is now called the Saros cycle, and the Babylonians found it in their own data, by counting. It changes everything, because it means an eclipse can be predicted. Not perfectly, and not always as to whether it will be visible from your particular city, but well enough to say that the dangerous period is coming and to prepare. And how they prepared tells you a great deal about how seriously they took all of this. If the omens indicated that the king was in mortal danger, they would perform the substitute king ritual. A man, sometimes a prisoner, sometimes a gardener, would be dressed in the royal robes and installed on the throne with all the proper ceremony, while the actual king went and lived quietly somewhere as a private person and was addressed as the farmer. The substitute would reign for the dangerous period, usually 100 days, absorbing whatever the gods intended. And then he was put to death and given a royal funeral, and the real king came back. There is a record of one occasion when the real king died of natural causes during the substitution, and the substitute simply stayed on the throne and reigned. That is the world in which this astronomy was done. Not detached, not academic. Life and death at the highest level of the state. Now watch what happens across the last few centuries before our era, because this is where the Babylonians did something genuinely new in human history. They stopped needing the omens to do the mathematics. Over generations, working with nothing but arithmetic and enormous quantities of observational data, Babylonian scholars developed methods for calculating in advance where the moon and the planets would be. Not by building a model of what the solar system physically looked like, which they never attempted, but by finding the numerical rhythms in the data and extending them forward. They worked out the length of the lunar month to within a couple of seconds of the modern value. They discovered the 19-year cycle in which the lunar and solar calendars come back into agreement, and used it to regulate their calendar, and it is still used to fix the date of Easter and the Jewish festivals today. They developed techniques for handling the changing speed of the moon through the month that are, in effect, a form of numerical integration, and a tablet from Babylon has been shown to compute the distance Jupiter travels by calculating the area under a graph of its velocity. which is a way of thinking nobody in Europe would do for another 14 centuries. And they did the whole thing in base 60. That is why there are 60 seconds in a minute, and 60 minutes in an hour, and 360 degrees in a circle. Every time you look at a clock, you are using a Mesopotamian number system, chosen because 60 divides neatly by a great many things, and passed down through Greek astronomy and Islamic astronomy into ours, without ever being replaced. The last thing they gave us is the one people know without knowing where it came from. Somewhere around the 5th century before our era, Babylonian astronomers took the band of sky through which the sun and the moon and the planets travel, and divided it into 12 equal sections of 30 degrees each. 12, because there are roughly 12 lunar months in a year. Equal, because equal sections make the mathematics work, whereas the actual constellations along that band are wildly uneven in size. They named the 12 sections after the constellations that happened to be there, most of which had already been named centuries earlier. The bull, the lion, the scorpion, the twins, that is the zodiac. It was invented as a coordinate system, a way of specifying position along the ecliptic so that calculations could be written down and compared. It has been doing other work ever since, but that is what it was built for. Picture the man doing it. He is sitting on a roof in the warm dark, with a small oil lamp shielded, so it does not spoil his eyes. There are date palms below, and the smell of the marshes, and somewhere out on the plain a dog. He has a lump of damp clay in one hand, and a cut reed in the other, and he is pressing wedge-shaped marks into it by feel, in the dark, because he has done it 10,000 times. He believes he is reading the intentions of gods. What he is actually doing is building, one night at a time, across generations of men who will never meet each other, the longest scientific data set in the ancient world, and inventing, without meaning to, the idea that the future behavior of the heavens can be calculated in advance. The tablet dries, it goes into the archive. The archive is buried under a city that becomes a mound in a flat plain, and it waits there in the dark for 2,500 years, unread, perfectly legible, until somebody digs it up. The Greeks inherited all of it. That is the first thing to understand about Greek astronomy, and it is not a criticism. Greek writers said so themselves, quite openly. The observations came from Babylon. The geometry of the calendar came from Egypt. And the Greeks were perfectly aware that they were arriving late to a subject that older civilizations had been working on for 1,000 years. What they did with the inheritance was something nobody had done before. They asked why. Babylonian astronomy was arithmetic. Give it a date and it will tell you where Jupiter is, with real accuracy. And it does not contain a single sentence about what Jupiter is, or what it is doing up there, or what sort of object it might be. That question was simply not part of the enterprise. The Greeks could not leave it alone. Set the scene, because it matters. This is a world of islands and headlands and a sea that is visible from almost everywhere. The light is hard and clear. The hills are dry, and smell of thyme and dust and hot pine resin in the afternoon. And there are olive trees with their undersides, showing silver when the wind moves through them. It is a world of small cities that argue with each other constantly, of men who sit outside in the evening cool and dispute things for the pleasure of disputing them, and of a language that had recently acquired an alphabet simple enough that a merchant or a farmer might learn it. Nobody here has a priesthood with a monopoly on the sky. That absence turns out to matter enormously. The story usually starts with Thales of Miletus in the 6th century before our era, who is supposed to have predicted a solar eclipse. The claim is doubtful, and the details are unrecoverable. But what Thales genuinely represents is the beginning of a habit. He tried to explain the world using the world, without gods in the explanation. Then Pythagoras, or the school that formed around him, and here two ideas emerge that will run for 2,000 years. The first is that the Earth is a sphere, not flat. This is worth pausing on, because there is a persistent modern belief that everyone thought the Earth was flat until Columbus, and it is simply untrue. Educated Greeks knew the Earth was round by the 5th century before our era, and the knowledge was never subsequently lost in the learned world. Medieval scholars knew it, Dante knew it. It was not controversial. The evidence was in front of anyone who looked. A ship going out to sea disappears hull first and mast last, which happens on a curve and not on a plane. Travel north, and new stars appear over the northern horizon, while familiar ones sink in the south. And during a lunar eclipse, the shadow the Earth throws on the moon is always the arc of a circle, from every angle, at every time of year, which only a sphere can manage. The second Pythagorean idea is stranger and more beautiful. They noticed that a vibrating string, stopped at simple whole number ratios of its length, produces the intervals we hear as harmonious. Half the string gives the octave, 2/3 gives the fifth. Number, they concluded, is not a description laid on top of the world. It is what the world is made of. And if that is true of a string, it should be true of the heavens, which move in circles at fixed speeds. There ought to be a mathematics of the sky, and the sky ought to be, in some sense, in tune. The phrase that came out of it, the music of the spheres, has been reduced to a poetic decoration. It was not meant as decoration. It was a serious claim about the structure of reality, and it turned out to be right in a way its authors could not have imagined, because the universe is in fact describable in mathematics, to an extent that still makes physicists uncomfortable. Plato, in the 4th century, set the problem that Greek astronomy would spend the next 500 years trying to solve. The heavens are perfect, he argued, and the only perfect motion is uniform motion in a circle. Therefore, all celestial motion must be built from uniform circles, which is a lovely idea, and it collides immediately with what anybody can see. The planets do not move uniformly. They speed up and slow down. Worse, at intervals, each of them stops in the sky, reverses, travels backwards against the stars for weeks or months, stops again, and resumes forward. The word planet comes from the Greek for wanderer, and the wandering is embarrassing if you have just claimed the heavens are perfect. So Plato posed the challenge, and it has come down in a memorable phrase: save the appearances. Find a system of uniform circular motions that produces, as its result, the messy behavior we actually observe. Everything that follows in Greek astronomy is an attempt to answer that. Aristotle built the physical version, a spherical Earth, unmoving, at the center. Around it, a nest of transparent spheres, one inside the other, carrying the moon, the sun, the planets, and the fixed stars, all turning. Below the moon, the realm of change and decay and the 4 elements. Above the moon, a 5th element, unchanging and eternal. That model held for nearly 2,000 years, and it is easy now to be condescending about it. Do not be. It fits the observations available at the time. It explains why things fall. It accounts for the fixed pole and the wheeling stars. It is coherent, testable against the sky, and wrong for subtle reasons that would take telescopes to expose. Not everyone accepted it. In the 3rd century before our era, Aristarchus of Samos proposed that the sun sits at the center and the earth goes round it and turns on its axis daily. That is heliocentrism, 18 centuries before Copernicus, and it was rejected, and the reasons for rejecting it were good ones. If the Earth is moving in an enormous orbit, the nearer stars should appear to shift position against the further ones over the course of the year. That shift is called parallax, and it was not observed. Aristarchus said the stars must be unimaginably far away. That seemed absurd. He was right. The parallax of even the nearest star is so small that it was not measured until 1838 with a telescope. The Greeks made the correct deduction from the available evidence, and the evidence was insufficient. Then Eratosthenes, librarian at Alexandria, measured the earth. He knew that at Cyane in the south, at noon on the summer solstice, the sun stood directly overhead and shone straight down a well without casting a shadow. At Alexandria on the same day, a vertical rod did cast a shadow, and the angle worked out at about 1/50th of a circle. So Alexandria and Cyane must be 1/50th of the Earth's circumference apart. He knew the distance between them. He multiplied. His answer was within a few percent of the true figure, and possibly much closer, depending on the length of the unit he used, which we cannot now be certain of. A man with a stick, a well, and the assumption that the Earth is round, measured the planet from a library. Hipparchus of Nicaea, in the 2nd century, is the one professional astronomers tend to admire most. He worked with Babylonian records, which had become available after Alexander, and combined them with Greek geometry, and he was rigorous in a way nobody had been before. He compiled a catalogue of around 850 stars with their positions. He introduced the system of ranking stars by brightness in 6 classes, first magnitude, down to 6th, which astronomers still use in modified form. And he found something nobody was looking for. Comparing his own measurements of a star's position against records made a century and a half earlier, he found a discrepancy, not an error, a systematic drift. The whole celestial sphere appeared to be very slowly rotating against the framework of the seasons, by about 1 degree every 72 years. That is the precession of the equinoxes. The Earth's axis wobbles like a spinning top, taking about 26,000 years to complete one circuit. So the pole star changes over the millennia, and the constellations slide gradually against the calendar. He detected a 26,000-year cycle from 150 years of data, with no instruments beyond sighting devices and his own eyes, by noticing that a number was slightly wrong. Which brings us to Claudius Ptolemy, in Alexandria, in the 2nd century of our era. Ptolemy pulled the whole tradition together into one enormous book, and he did it so comprehensively that everything before it stopped being copied and was largely lost. The book was called the Mathematical Treatise, and it reached us through Arabic, where it acquired the name it still has, the Almagest. Inside it is the complete geocentric system, worked out in full mathematical detail. The Earth at the center, each planet riding on a small circle, an epicycle, whose own center travels round a larger circle, a deferent, adjust the sizes and speeds, and the backwards loops fall out of the geometry naturally. It was complicated. It required additional devices to fit the observations. It was also, and this is the point, accurate. It predicted planetary positions well enough for practical purposes for 1400 years, and it was used, and it worked. That is the uncomfortable lesson sitting in the middle of this story. A model can be wrong in every structural respect, and still generate correct predictions for centuries. Fitting the data is not the same as being true, and the Greeks proved it more thoroughly than anyone. And then there is the object that changes how we think about all of this. In 1900, sponge divers sheltering from a storm off the tiny island of Antikythera, between Crete and the Peloponnese, went down onto a reef and found a wreck. It was a Roman-era ship from around the 1st century before our era, and it was carrying cargo: bronze statues, marble, glassware, coins. Among the material brought up was a corroded lump about the size of a large book, which cracked open some months later in the museum and was found to contain bronze gear wheels. Nothing remotely like it exists from anywhere for the next 1,000 years and more. Decades of work, and eventually X-ray tomography that could see through the corrosion, have established roughly what it was. At least 30 interlocking bronze gears, some with teeth cut to a fraction of a millimeter, driven by a hand crank. Set the date, and dials on the front and back show the position of the sun and moon in the zodiac, the phase of the moon, the state of the lunar and solar calendars, the timing of eclipses, and the 4-year cycle of the athletic games. There is a differential gear arrangement in it. There is a pin and slot mechanism that deliberately makes one wheel turn at a varying rate to reproduce the changing speed of the moon through its month, which means whoever built it knew that the lunar motion is not uniform and had worked out how to model it mechanically. It is a mechanical model of the sky, and it is more than 2,000 years old. The honest question is not how they built it, since we can now see how it works. The honest question is, what else there was? Nobody makes an object of that sophistication as a first attempt. There must have been a tradition, a workshop, predecessors, apprentices, other machines. We have exactly one, and we have it only because a ship sank, and because a storm forced some divers onto that particular reef 19 centuries later. Everything else went into the melting pot, because bronze is valuable, and old machinery is scrap. The sea is very dark over that reef, and very deep, and the wreck is still down there in the cold with the rest of its cargo, and divers still go back to it, and things still come up. Rome was not much interested in why. The Romans took Greek astronomy the way they took Greek sculpture and Greek architecture, which is to say wholesale, appreciatively, and without adding a great deal to the theory. What they did instead was use it, on a scale nobody had managed before, to run an empire. Their own relationship with the sky was older and stranger than the Greek one, and it never went away. Before any significant public act in Rome, somebody had to take the auspices. An official called an augur would mark out a rectangle of sky using a curved staff and then watch it. Birds were the primary sign. Which birds, from which direction, flying or feeding, how many, in what order. There were rules, and the rules were written down, and the interpretation was a technical profession with a literature. If the signs were wrong, the business did not proceed. Assemblies were dissolved, elections were annulled, armies did not march. Before a battle, the sacred chickens were consulted. If they ate greedily, the omens were good. If they refused their feed, they were not. There is a famous story of a Roman commander at sea whose chickens would not eat, and who threw them overboard, remarking that if they would not eat, they could drink instead. He lost the battle, and the story was told for centuries afterwards, which tells you how the Romans felt about it. You should not read this as simple superstition, or at least not only as that. The auspices were also political machinery. A magistrate, who wanted to block a piece of legislation, could declare that he had observed unfavorable signs, and the business stopped. It was a constitutional break dressed in feathers, and everyone involved understood the game perfectly well, while also, quite genuinely, believing in it. The Roman calendar, meanwhile, was a shambles. It was lunar in origin, it did not match the sun, and it was corrected by intercalation, which is to say by adding an extra month when required. The decision on when to add it belonged to the College of Priests, and the priests were politicians, and the length of the year affected how long people held office and when debts fell due. The result was exactly what you would expect. Years were extended to keep friends in office and shortened to remove enemies. By the middle of the 1st century before our era, the calendar had drifted so far out of true that the harvest festivals were happening months away from the harvest, and no one could say with confidence what date it actually was in relation to the seasons. Julius Caesar, who had spent time in Egypt and seen a solar calendar working properly, fixed it, advised by an Alexandrian astronomer named Sosigenes. He abolished the lunar basis entirely and adopted a year of 365 days, with an extra day every 4th year. Months of 30 and 31 days, with a short February, arranged so as to add up. To get everything back into alignment before starting, the year we call 46 before our era was given 445 days. It is the longest year in recorded history, and the Romans called it the Year of Confusion. That calendar, with one later adjustment to the leap year rule, is the calendar on your wall. The months you use are Roman months. July is named after the man who reformed it. The whole structure of your working year comes from a dictator's decision to stop the priests from cheating. At sea, the Romans were competent rather than adventurous. Mediterranean sailing was mostly coastal. You went from headland to headland, kept the land in sight where you could, and anchored or beached at night when possible. There were sailing directions describing coastlines, harbors, landmarks, and dangers, and a good captain carried them in his head. For the open crossings, they used the sky, the pole star for direction, the sun for east and west, the wind, which in the Mediterranean is fairly predictable by season, and the swell, and they observed the sailing season strictly. From roughly November to March, the sea was considered closed. Not by law exactly, but by universal practice, because the winter storms were lethal, and the overcast skies took away the stars, and a ship that cannot see the sky in a storm is a ship that does not know where it is. There is one moment in Roman military history where astronomy steps in directly, and it is worth telling. In 168, before our era, on the night before the Battle of Pydna in Macedonia, the moon was eclipsed. An eclipse before a battle is about as bad an omen as a Roman army could receive, and the men were frightened. A tribune named Gaius Sulpicius Gallus, who had studied the subject, went among the troops and explained beforehand that it was going to happen, and why, describing it as a natural event with a known cause and no bearing on their fortunes. The Romans held steady. The Macedonians, who had not been told, took it as a sign that their king was finished. The Romans won the next day. What is interesting is not the outcome, but that a Roman officer in the 2nd century before our era could predict a lunar eclipse and explain the mechanism to ordinary soldiers, and that this was considered a useful thing for a commander to be able to do. Now travel east, a long way east, to a different sky, and a very different mathematics. Indian astronomy is one of the great traditions, and it is chronically underrepresented in tellings of this story, partly because so much of it came to Europe through intermediaries who did not always say where it came from. It begins in the Vedic period, with a division of the sky that is quite unlike the Greek one. The Indian system tracks the moon rather than the sun. The moon moves through the background stars, completing a circuit in about 27 1/3 days, and Indian astronomers divided its path into 27 segments, each roughly 1 day's travel. Those are the nakshatras, usually translated as lunar mansions. Each has a name, a presiding deity, an associated star or group of stars, and a character. It is an elegant scheme, because it fits what the moon actually does. On any night, you can look up, see which nakshatra the moon is sitting in, and know where you are in the lunar month without counting anything. The nakshatras appear in the earliest Sanskrit texts, and they are still used today, for religious observance, for festival dates, and for the timing of weddings, which means it is one of the oldest continuously functioning sky systems on the planet. Timekeeping in the Indian tradition went in the other direction from most, which is to say towards the very large and the very small simultaneously. At one end, units of time down to fractions of a second. At the other, cosmological cycles of enormous length, running to millions and then billions of years, with the universe going through vast repeating ages of creation and dissolution. That is a striking thing to find in a text well over 1,000 years old, in a world where most cosmologies were working with a few thousand years, and it was arrived at for religious rather than observational reasons, and it should not be overinterpreted. But the willingness to think in those magnitudes is real, and it is rare. The technical astronomy is set out in a group of works called the Siddhantas, and then transformed by a series of individual mathematicians whose names we have. Aryabhata wrote in the year 499, aged 23, a compact and extraordinary work. He stated that the Earth rotates on its axis, and that the apparent daily turning of the stars is caused by that rotation, rather than by the sky moving. He compared it to a man in a boat on a river who sees the bank slipping backwards. He explained eclipses correctly as shadows. The moon passing into the shadow of the earth, or the moon's own shadow falling on the earth. This was a direct rejection of the traditional account in which a demon swallows them, and he said so, and it caused argument. He knew the moon shines by reflected sunlight. He calculated the length of the sidereal year to within a few minutes of the modern value, and he produced a table of sign values, which is a fundamental piece of trigonometry, and the word sign itself has a history that runs from Sanskrit through Arabic to Latin, with a mistranslation somewhere in the middle, involving a word for a bay or a fold of a garment. Then Brahmagupta, in the 7th century, working in Rajasthan. He wrote a treatise on astronomy that contains, along the way, the first surviving systematic account of zero as a number in its own right, with rules for calculating with it. Not zero as a placeholder in writing numbers, which others had, but zero as a thing you can add and subtract and multiply. He also gave rules for negative numbers, describing them in terms of fortunes and debts. Those ideas, together with the decimal place value system, traveled west into the Islamic world, where they were taken up and extended, and from there into Europe, where they arrived as what Europeans called Arabic numerals. The digits you use to write down a phone number came from India. So did the zero at the heart of every calculation ever performed by any computer. None of it was developed for its own sake. It was developed because Indian astronomers needed to calculate planetary positions and eclipse timings and festival dates accurately. And the mathematics they built to do it turned out to be the foundation of nearly everything numerical that came afterwards. The air is warm and heavy, and there is a smell of dust and jasmine and cooking oil, and somewhere a temple bell. The moon has moved on into the next mansion, as it does every night, 27 of them in order, the same order it has followed since before anyone thought to write it down. In China, astronomy was a department of state, and getting it wrong could cost you your head. The reasoning behind that begins with a political idea called the mandate of heaven. An emperor did not rule because his father had ruled, or not only for that reason. He ruled because heaven had appointed him, and the appointment was conditional. If he governed well, heaven was content and the natural order held. If he governed badly, heaven withdrew its favor and the withdrawal would be announced. Announced how? By irregularity in the sky, an eclipse, a comet, a new star appearing where no star had been, a planet doing something unusual. These were not neutral events, they were public statements about the emperor's standing, visible simultaneously to every one of his subjects across an enormous territory, and they could not be suppressed. So the imperial court needed astronomers, badly, and it needed them to be right. If an eclipse could be predicted, the court could hold the correct ceremonies in advance, demonstrate that the emperor knew it was coming, and turn a threatening omen into a display of competence. If it arrived unannounced, the implication was that the ruler had lost touch with heaven. The Bureau of Astronomy was therefore a permanent institution of the Chinese state, staffed by professionals, funded continuously, and maintained through dynasty after dynasty for more than 2,000 years. There is an old story, probably legendary, about two court astronomers called He Si and Ho, who got drunk and failed to predict an eclipse and were executed for it. The story is almost certainly a later moral tale rather than history. It survived because it expressed something true about the seriousness of the job. The consequence for us is the greatest continuous astronomical record on Earth. Because the observations were official, they were archived. Because they were archived, they went into the dynastic histories. And the dynastic histories were copied and recopied and preserved with a care that no other civilization applied to its records for anything like as long. The result is a run of Chinese sky observations, covering, with gaps, something close to 3,000 years. Modern astronomers use it. That is not a courtesy. It is a working data source, because there are questions about the long-term behavior of the solar system and the Earth's rotation that simply cannot be answered without observations from before the telescope, and China is where they are. Take comets. Chinese records describe what they called broom stars, with careful notes on the date of first appearance, the position, the direction of the tail, the path across the constellations, and the date it faded. Halley's Comet, which returns every 76 years, has been identified in Chinese records reaching back to 240 before our era. That is a continuous observational history of a single object across more than 2 millennia, which allowed later astronomers to reconstruct its orbit and the way it has been nudged by the planets over time. Then there is the night of the 4th of July, 1054. Court astronomers recorded a guest star in the constellation they knew as the Celestial Pass, near the star we call Zeta Tauri. It was extremely bright. The records say it was visible in daylight for 23 days, and that it remained visible at night for nearly 2 years before fading. A guest star is a star that arrives and then leaves. In a cosmology where the heavens are supposed to be permanent, that is a significant event, and they recorded it with the detail that significance demanded. We know now what they were looking at. A massive star, 6,000 light-years away, reaching the end of its life and collapsing and detonating. The material thrown off is still expanding, and we can see it, and it is called the Crab Nebula, and at its center is a neutron star, spinning 30 times a second. Almost nothing was written about it in Europe. There are a few possible references and nothing solid. Whether that is because of cloud, or because European observers were not looking systematically, or because the philosophical framework held that the heavens do not change, and therefore a new star was difficult to report, is argued about. The Chinese wrote it down because writing it down was their job. The mapping was equally systematic. Astronomers named Shi Shen and Gan De, working in the 4th century before our era, produced star catalogues, among the earliest anywhere. And in a sealed cave at Dunhuang on the edge of the Gobi Desert, among tens of thousands of manuscripts walled up around the 11th century and not opened until 1900, there was a scroll of paper more than 2 meters long, covered in stars. The Dunhuang Star Atlas dates from around the year 700. It shows over 1,300 stars in 12 panels, plus a circumpolar chart, drawn with a projection that handles the curvature of the sky sensibly, in 3 colors, to indicate which of the old schools had catalogued each star. It is the oldest complete star atlas known from any civilization. The Chinese sky itself was organized differently from the Mediterranean one, where the Greeks built their system around the band of the zodiac, following the sun. The Chinese built theirs around the pole. The pole is the still point. Everything turns around it. And in a political cosmology, the still point around which everything turns is the emperor. So the circumpolar region was the purple forbidden enclosure, the celestial palace, containing the emperor's throne and his family and his officials, mirroring the layout of the palace on the ground. Beyond it were further enclosures, and then the 28 lunar lodges spread around the sky, uneven in size, marked out by reference stars. The sky was a bureaucracy. There are stars for the imperial secretariat, stars for the granaries, stars for the market, stars for the cavalry, which sounds quaint until you remember that the Greeks put a hunter and a bear and a chained princess up there, and that neither arrangement is more natural than the other. Every culture looks up and sees itself. The instruments were bronze and beautiful, and some of them still exist. Armillary spheres, which are nested rings representing the great circles of the sky, mounted so they can be turned and sighted along, were built in China from at least the 1st century and refined continuously. In 1092, a scholar and official named Su Song completed a water-driven astronomical clock tower in Kaifeng, about 10 meters tall. Inside, a great wheel turned by water in carefully measured buckets drove an armillary sphere on the roof, a celestial globe on the floor below, and a set of doors from which figures emerged to announce the hours by striking bells and holding up tablets. The escapement mechanism in it, which lets a wheel advance one step at a time, is a genuine ancestor of the mechanical clock. The tower was dismantled when the capital fell to invaders a few decades later, and the parts were carried north, and it was never successfully rebuilt because the men who understood it were gone. Susong's written description survived, with drawings, which is the only reason we know what it was. 2 centuries later, under the Mongol emperors, an astronomer named Guo Shoujing rebuilt Chinese astronomy from the instruments up. He designed simplified instruments that abandoned the tangled, nested rings of the armillary sphere in favor of separate, larger, more accurate devices. He organized a survey with observing stations spread across the whole empire, from the far south to the edge of Siberia, taking measurements simultaneously. And he produced a calendar that gave the length of the year as 365.2425 days. That is correct, to within about 26 seconds. It is the same figure adopted in Europe by the Gregorian Reform, 300 years later. The observatory platform he worked from still stands in Beijing, a squat brick tower with bronze instruments on the roof. And if you go up there now, you look out over a city of 20 million people, under a sky in which, on a normal night, you can see perhaps a dozen stars. The instruments are still pointing at them. Cross an ocean now, to a place where the sky is often hidden by the trees. The lowland forest of the Yucatan and Guatemala is hot and wet and loud. The humidity does not drop much at night. There is a constant sound of insects, and periodically the roar of howler monkeys, which is one of the more alarming noises in nature and carries for miles. The ground is limestone, porous, so that rain vanishes into it and there are almost no rivers. Water comes from sinkholes, where the rock has collapsed to expose the water table, and those holes were sacred, and the cities were built around them. You cannot see much sky from the forest floor. The canopy closes overhead, which is one reason why Maya cities are full of tall stone platforms with nothing on top but a small building and a view. Get up there, above the trees, and the sky opens out completely. Warm air, the forest below going on in every direction, black, and the calling of things in it. The stone still holding the day's heat under your hands. And overhead at that latitude, a sky that includes almost everything, because from the tropics you see both the northern and southern constellations across the course of a year. The Maya watched it with a precision that took the modern world a very long time to acknowledge. Their calendar system was not one calendar but several, running simultaneously, interlocking. There was a cycle of 260 days, made of 13 numbers, turning against 20 named days, so that each combination came round once in 260. Nobody is certain where that number comes from. It is close to the human gestation period. It is also the interval between the 2 days each year when the sun passes directly overhead at the latitude of certain Maya cities. Both explanations have supporters. There was a second cycle of 365 days, the approximate solar year, 18 months of 20 days, plus 5 days at the end, which were considered dangerous, and during which people avoided doing anything important. Run the two together and they come back into the same alignment once every 52 years. That period, the calendar round, was the great unit of Mesoamerican life. And then, because 52 years is not long enough to date a monument in a way that will never be ambiguous, the Maya built the long count. The long count is a linear tally of days from a fixed starting point in the distant past, corresponding to a date in August of 3114 before our era. It counts in units of days, 20 days, 360 days, 7,200 days, and 144,000 days, and it can be extended upwards indefinitely. They carved these dates onto stone monuments, and they run to millions of days, and there are inscriptions that reach back billions of years and forward to dates far beyond any human concern. To operate a system like that, you need positional notation, and you need a symbol for nothing. The Maya had zero, independently, centuries before it reached Europe. They wrote it as a shell. Now, the planet. Venus is the brightest thing in the sky after the sun and the moon, and it behaves in a way that is impossible to ignore once you start paying attention. It appears in the west after sunset, climbing higher over months, becoming brilliant. Then it drops back towards the sun and disappears. After a short absence, it comes back on the other side, rising before dawn in the east as the morning star, and goes through the same performance in reverse. Then it vanishes again, this time for a much longer stretch, and eventually returns to the evening sky. The whole cycle takes 584 days. The Maya knew that number, and they knew it very precisely. In one of the 4 surviving Maya books, the Dresden Codex, there is a set of tables devoted entirely to Venus, tracking its appearances and disappearances across long periods and including a correction scheme to prevent the tables from drifting out of true over centuries. The value implied by their tables is accurate to within a couple of hours across the full cycle. They did that by counting sunrises across generations and writing it down. And Venus mattered to them in a way it did not to most other cultures. Where the Mediterranean world made it a goddess of love, the Maya associated it with war, danger, and sacrifice. Its first reappearance as the morning star, after that long absence, was a particularly hazardous moment. The Codex specifies who will be harmed on each occasion. There is evidence that some military campaigns were timed to the Venus cycle. Archaeologists have found correspondences between the dates of recorded conflicts and specific Venus events, and while the pattern is debated in its details, the general association between that planet and warfare is well established from the texts themselves. At Chichen Itza there is a building unlike anything else on the site. Most Maya architecture is rectilinear. This one is round, a cylindrical tower on a broad platform, and inside it, a spiral staircase climbs to a small chamber near the top. The Spanish called it El Caracol, the snail, because of the stair. The upper chamber has narrow windows. Most of the building is damaged and much has fallen, but of the sight lines that can still be measured, several correspond to significant positions of Venus on the horizon, including its northern and southern extremes of setting. Others appear to relate to the sun at the equinoxes. There is honest scholarly argument about how many alignments are intentional and how many are coincidental, because with enough windows and enough celestial targets, some matches will occur by chance. But the building is round, which is rare and deliberate. Its windows are few and awkwardly placed for any practical purpose, and it sits in a civilization that we know from its own books was tracking Venus obsessively. Whatever else it was, people went up that spiral stair in the dark to look at something. Picture it. The stone is cool, the stair is narrow, and turns tightly, and you are going up it by torchlight, and the smell is smoke and copal resin and damp limestone. At the top, the air moves a little. You put your eye to a slot in the wall, and framed in it, low over the forest, is a single very bright point of light, exactly where the tables said it would be, on the night they said it would be there. The Maya cities were largely abandoned centuries before Europeans arrived, for reasons involving drought, warfare, and political collapse that are still being worked out. The forest took them back. The books were destroyed later, and deliberately. In 1562, at Mansi in the Yucatan, a Franciscan named Diego de Landa held a ceremony in which Maya manuscripts and religious objects were burned. He wrote afterwards that the books contained nothing but superstition and lies of the devil, and that the people to whom they belonged regretted their loss to a degree that caused them great affliction. 4 Maya codices survive. 4. Out of a literature that must have run to thousands of volumes covering astronomy, history, ritual, and medicine. De Landa also, and this is the bitter irony, wrote a detailed account of Maya culture, including a partial guide to the writing system, which turned out centuries later to be one of the keys that allowed the script to be deciphered. Move northwest now, up into the high valley of central Mexico, and the climate changes completely. Tenochtitlan sits at over 2,000 meters. The nights are cold and dry, and startlingly clear. The city was built on islands in a lake, connected by causeways, with canals running through it, and mountains standing round the whole basin, 2 of them volcanoes, with snow on top. The Aztecs inherited the Mesoamerican calendar system, the 260-day count, and the 365-day year, and the 52-year round, and they gave the end of that round a ceremony of extraordinary weight. They believed the world had been created and destroyed 4 times already, and that they were living in the 5th creation, which would also end. The end could come at the close of any 52-year cycle. So in the last days of a cycle, the city was prepared for a possible ending. Fires were put out, everywhere, every hearth in every house across the whole valley. Cooking vessels and household images were broken and thrown away. Pregnant women were shut in granaries, and children were kept awake and walked about, because it was believed that anyone who slept might be transformed. Then, after dark, a procession of priests went out of the city and up a hill called the Hill of the Star, and waited on the summit. What they were waiting for was the Pleiades. The observation was of that small cluster crossing the meridian, the highest point of its passage, at midnight. If it crossed and continued on its way, the world would go on, and another 52 years had been granted. At the moment it passed, a fire was kindled on the summit by friction, in the chest cavity of a sacrificial victim, and once it caught, runners carried torches down from the hill and out along the causeways into the city and beyond, and every temple and every household relit its hearth from that single flame. Consider what that looked like from a distance. A completely dark valley, a city of 250,000 people with no light in it at all, silent, and then one point of fire on a hilltop, and then a line of moving lights coming down the hill, and then that line branching, and branching again, spreading out across the whole basin, until the darkness was replaced house by house over the course of a night. The Aztec sunstone, that great carved disc in the museum in Mexico City, which is universally called the Aztec calendar, is worth a note of correction. It is not a working calendar. It carries calendrical signs, including the 20-day names around the inner ring, but its subject is cosmological. At the center is a face, surrounded by the symbols of the 4 previous world ages, and the whole thing is a statement about the creation and destruction of suns, rather than a device for telling the date. It was buried after the conquest, and lay under the main square of Mexico City for 2.5 centuries, before being dug up during repaving work. The Templo Mayor stood at the center of Tenochtitlan, with 2 shrines side by side at the top, one to the rain god and one to the war god, and there is good evidence that the whole structure was oriented so that around the equinoxes the sun rose in the notch between them, seen from the ceremonial precinct below. Spanish soldiers described the view from the top of it, before they pulled it down, and the description survives, and it is one of the few glimpses we have of that city as it actually looked. The lake has been drained. The temple is a foundation in a hole beside a cathedral built from its stones. And the Pleiades still cross the meridian at midnight on the same nights, above a city with rather more lights in it now, watched by nobody in particular. Now the hardest navigation problem any human being has ever solved. The Pacific covers 1/3 of the surface of the planet. You could drop every landmass on Earth into it, and have room left over, and scattered across it, mostly in the western and central regions but reaching out to the far corners, are islands, and many of them are tiny. Some are volcanic and mountainous, and can be seen from 30 miles away. Many are atolls, rings of coral a few meters above the water, invisible from more than about 10 miles even in perfect conditions. Between them, in some cases, are 2,000 miles of open ocean. And people got there, all of it. Every habitable island group in the Pacific was settled before Europeans arrived, by people sailing double-hulled canoes against the prevailing winds for much of the route, without a compass, without a chart, without a clock, and without any instrument of any kind. For a long time, Europeans could not accept that this had been done deliberately. There was a persistent theory that the islands had been populated by accident, by fishermen blown off course, drifting until they hit something. That theory is dead, and it deserved to die. Drift voyages will not populate the Pacific. The winds and currents are wrong for it. The survival odds are hopeless, and you cannot found a colony with a boatload of men who happen to be out fishing. Settlement required deliberate expeditions carrying men, women, children, breeding animals, and seed crops, sailing purposefully into the unknown, and, crucially, being able to get home again to report. They navigated. They did it with a system, and the system was taught, and in some places it survived. At the center of it is the star compass. Here is the key insight. A star rises at a fixed point on the eastern horizon and sets at a fixed point on the western horizon, and those points do not change through the year, and they do not change through a human lifetime. Where a star rises depends only on the star and on your latitude. So the horizon can be divided up, not into degrees, but into named houses, each associated with the star, or stars, that rise and set there. A navigator memorizes the entire system. In some traditions, this means well over 150 stars, with their rising points, their setting points, and the sequence in which they follow each other up. That last part is what makes it work at sea. A star is only useful for steering when it is low, near the horizon. Once it climbs, its bearing changes, and it becomes useless. So the navigator holds a course on a star for perhaps an hour, and when it lifts too high, he switches to the next star that rises out of the same house behind it, and then the next, following a star path across the whole night. He is essentially steering by a sequence of temporary compass needles, each of which he must know by heart, in order, for every direction, for every season. Then the sky clouds over, and the whole system disappears, which is why the stars are only one part of it, and by many accounts not the most important part. Underneath the canoe, there is the swell. Ocean swell is not the same as wind waves. Wind waves are local and confused and change with the weather. Swell is generated by distant weather systems and travels enormous distances in a steady direction. And in the Pacific, the dominant swells hold their bearing for weeks at a time. A navigator learns to feel them, not to see them, though he does that too. To feel them through the hull, in his body, often lying down in the middle of the canoe where the motion is clearest. There will typically be several swells running at once from different directions, crossing each other, and an experienced navigator can distinguish them and hold a course by the angle at which the boat meets them. In cloud, in rain, at night, with nothing visible at all. That skill takes decades to acquire, and it is the reason the system does not collapse in bad weather. Then there is the reading of things near land, which extends the target enormously. An atoll 10 miles wide is a small thing to hit across 2,000 miles of ocean, but an atoll is not just the land, it has a zone around it, and that zone can be 40 or 50 miles across. Birds are the clearest sign. Certain seabirds, noddies and white terns among them, sleep on land and fish at sea. In the morning they fly out, and in the evening they fly back. Find those birds late in the day, watch which way they are heading, and you have a bearing to an island you cannot see, and a good idea of the distance. Clouds behave differently over land. They pile up over a high island and hold station while other clouds move past. Over a lagoon, the underside of a cloud can take on a faint greenish tint reflected from the shallow water, and a navigator, who knows what he is looking for, can read the presence of an atoll from the color of the bottom of a cloud. Swells refract and reflect around islands, producing interference patterns in the water that can be detected from some distance downwind. And the Marshall Islanders made teaching devices out of sticks and shells to model exactly those patterns. There are also reports of a phenomenon called te lapa, described as flashes of underwater light that appear to point towards land from considerable distances. It is discussed in the literature and by navigators, and it has never been satisfactorily explained or confirmed by measurement, so it should be filed as an unresolved claim rather than an established technique. Holding all of this together is a way of thinking about position that is genuinely different from ours. In the system recorded in parts of Micronesia, called Etak, the canoe is imagined as stationary. The navigator holds his starting island astern, his destination ahead, and a third reference island off to one side. And as the voyage proceeds, he tracks the movement of that reference island backwards along the star houses. The canoe does not move. The islands move past it. Position is not a coordinate on a grid, but a stage in a sequence. It is not how we think about space, and it works. Now put yourself in it. You are 5 days out. There has been no land since the second morning. The canoe is running with the swell on the port quarter, and the hulls are making a steady rushing noise, and there is spray coming over occasionally, warm, and the smell is salt and wet lashings, and coconut oil, and the sennet rope that holds the whole vessel together, because there is not a single nail in it. It is dark, the sail is a black shape above you. Somebody is bailing, slowly, with a wooden scoop. The navigator has not slept properly in 5 days. He cannot. If he sleeps deeply, he loses the thread, because there is nothing external holding his position, no instrument recording it. It is all in his head, continuously updated, every hour, for the entire voyage. He watches a star lift out of the sea ahead, holds it for a while, lets it go, takes the next one. And in 3 days, if everything he has done is right, there will be a line of cloud on the horizon in the afternoon that does not move. By the 20th century, almost all of this had been lost. The voyaging traditions had ended across most of Polynesia under colonization and missionary pressure, and the arrival of European ships, and the knowledge went with the last of the navigators who held it. In the 1970s, a group in Hawaii built a replica double-hulled voyaging canoe and named her Hokulea, after the star Arcturus, which passes directly overhead at the latitude of Hawaii. They needed a navigator, and there was nobody left in Hawaii who could do it. They found one on Satawal, a tiny island in the Caroline group in Micronesia, one of a handful of places where the tradition had survived unbroken. His name was Mau Pialug. He had been initiated as a navigator as a young boy, and had been taught in the old way, by his grandfather, lying in tide pools to feel the swell. He agreed to take them to Tahiti, 2,400 miles, no instruments. They left in 1976 and arrived 33 days later, and there were 17,000 people waiting on the beach. Mauk went on to teach a generation of Hawaiians, breaking with the tradition that the knowledge stayed within his own island and family, because he could see that if he did not, it would die with him. There is one more figure worth naming, from 200 years earlier. When Captain Cook reached Tahiti in 1769, a high priest and navigator called Tupaia joined the endeavor and sailed with her. Tupaia produced a chart, drawn with European help, and considerable confusion on both sides about how the two systems of representation related to each other, showing dozens of islands across a span of thousands of miles of the Pacific. He acted as pilot and interpreter, and the Englishman noted with astonishment that at any point in the voyage, in any weather, he could be asked to point towards Tahiti, and he would point, immediately, and be right. He died of disease at Batavia on the way home, and much of what he knew was never written down. The sea is very warm. The canoe lifts and drops, and if you close your eyes, you can feel exactly which way the swell is running, and which way you are crossing it. And the star you were steering by an hour ago has climbed too high to be of any further use, and has been let go. There is another one coming up out of the water behind it. The Northern Ocean is a different problem entirely. Cold, first. Cold enough that going into the water is a matter of minutes rather than hours. Grey water, grey sky, and a horizon that is frequently not visible at all, because the sea and the cloud have merged into the same thing. Fog, constantly. Rain that comes sideways. Ice further north, and the particular pale glare on the underside of low cloud that tells an experienced sailor there is pack ice below it, over the horizon, out of sight. And the sun, which in those latitudes in summer barely sets and never rises far, so that there are weeks of a long grey twilight in which there are no stars at all, for hour after hour. Into that, from the 8th century onwards, went open boats. Norse ships were superb. Clinker-built, with overlapping planks fastened to a light frame, they flexed with the sea rather than fighting it, and they were shallow enough to run up a beach and seaworthy enough to cross the Atlantic. The ocean-going cargo vessels, the Knarr, were broader and deeper than the raiding longships and could carry livestock and timber and families. They reached Iceland and settled it. They reached Greenland and settled that. And around the year 1000, they reached North America, 5 centuries before Columbus. And there is no argument about it, because the settlement site at Lonceau Meadows in Newfoundland was excavated in the 1960s, and the Norse buildings and ironwork are there. How did they find their way? Mostly by latitude sailing, which is the elegant solution to having no way of measuring longitude. The principle is simple. Get to the right latitude first, then turn and run along it. Latitude you can measure, because it is written in the sky. The height of the pole star above the horizon equals your latitude. Sail north and it climbs. Sail south and it sinks. Hold it at a constant height, and you are holding a line across the ocean. So the sailing directions preserved in the Icelandic sources are exactly that kind of instruction. Go north along the Norwegian coast to a known point, then west, keeping far enough south of Iceland that you see birds and whales from it, but not the land itself, and hold that course, and you will make Greenland. They also had refinements. The height of the sun at midday works the same way, if you know the date. There is an object found in Greenland, a broken wooden disc with lines scratched on it, which has been interpreted by some researchers as a sun compass, a bearing dial on which a central pin's shadow could be tracked against a curve to give direction. That interpretation is plausible and widely discussed but not certain, since the object is a fragment and there is only one of it. Which brings us to the sunstone, and here it is worth being careful, because this is one of the most repeated stories in popular history, and the evidence is thinner than the confidence. The sagas mention a solarstein, a sunstone, used to find the sun when the sun could not be seen. That is the textual basis, and it is slight, and the surviving references are brief. In 1967, a Danish archaeologist suggested that this might have been Iceland's spar, a transparent form of calcite, which is common in Iceland, and which has an unusual optical property called birefringence. Light passing through it splits in two, so you see a double image, and the relative brightness of the two images depends on the polarization of the incoming light. Sunlight scattered by the atmosphere is polarized in a pattern centered on the sun. So in principle, by rotating such a crystal and watching the two images, you could locate the sun through cloud or after it had set. Experiments have been done, and the method genuinely works, to within a degree or so, even under complete overcast. But no sunstone has ever been found on a Viking ship or in a Viking burial. Not one. A piece of Iceland spar was recovered from a wreck in the English Channel, which is suggestive, except that the ship was English and sank in 1592, more than 500 years after the Viking Age. So the honest position is this: the sagas mention something. A physical mechanism exists that would do the job. No archaeological evidence connects the two. It is a very good hypothesis, and it is not a demonstrated fact, and you should be a little suspicious of anyone who tells it to you as settled. There is one more complication worth knowing, because it changes the picture. Polaris was not the pole star then, not properly. Because of precession, that slow 26,000-year wobble of the Earth's axis, the north celestial pole moves, and in the Viking Age Polaris sat several degrees off it and made a noticeable little circle through the night, rather than sitting still. So Norse navigators were working with a north star that wandered, and they knew it, and they compensated. Which is a considerably harder thing than what a modern sailor does. Picture the situation the sagas describe more than once. A crew that has been at sea for days in thick weather, with no sight of sun or star, running on dead reckoning and instinct, in an open boat, in the North Atlantic. The word in Old Norse for that condition translates roughly as being lost at sea in fog, and it appears often enough to suggest it was a normal hazard rather than a rare disaster. The cold gets into everything. The wool is wet and stays wet. There is the smell of tar and wet sheep's wool and salt fish. Somebody is bailing continuously because a clinker-built hull always leaks a little, and the man at the steering oar is watching the sky for any thinning at all, and then a gap opens in the cloud, and one star comes through, and he knows which one it is, and he knows how high it should be, and he turns the ship. Now go south and east, into the warm and into libraries. From roughly the 8th century, the Islamic world became the center of astronomy on this planet, and remained so for something like 600 years. The reasons are partly religious and entirely practical. Islam requires prayer 5 times a day, and the times are defined by the position of the sun, which varies with latitude and season. It requires prayer facing Mecca, which means that from any point on a curved earth, you must be able to calculate a direction to a specific distant place. And it requires a lunar calendar, in which the start of each month depends on the visibility of the new crescent moon, which is a genuinely difficult problem in observational astronomy. 3 obligations, all of them mathematical, all of them binding on every believer in a territory that eventually stretched from Spain to Central Asia. That created continuous, well-funded demand for astronomers, and the demand was met. It began with translation. Under the Abbasid caliphs in Baghdad, a systematic effort was made to acquire and translate the scientific literature of the world into Arabic. Greek texts, Persian texts, Indian texts. Ptolemy came in from Greek. The Indian numerals and the astronomical Siddhantas came in from Sanskrit. For the first time, all of it was in one language, in one place, and could be compared. And then they got to work on it, and this is the part that popular accounts get wrong. The Islamic astronomers were not custodians who kept Greek learning warm until Europe was ready. They were practitioners who tested it, corrected it, and in places replaced it. Al-Battani, working in northern Mesopotamia around the year 900, made his own observations over decades and found that Ptolemy's figures were off. He corrected the length of the solar year, improved the value for the precession of the equinoxes, and produced tables that were still being used by European astronomers 700 years later. Al-Sufi, in the 10th century, wrote the Book of Fixed Stars, in which he went through Ptolemy's catalogue, constellation by constellation, checked the positions and magnitudes against his own observations, corrected what was wrong, and illustrated each constellation twice, as seen in the sky and as seen mirrored on a globe. In it, describing the region of the constellation we call Andromeda, he records a little cloud, a small nebulous patch, faint, visible to the naked eye from a dark site. That is the first known record of the Andromeda galaxy, a structure of 1 trillion stars, 2.5 million light-years away, noted in the 10th century as a small cloud by a man who could have had no idea what he was looking at. And then there is the astrolabe, which is the most beautiful scientific instrument ever made. It is a disc of brass, usually the size of a hand, and it is a flattened map of the sky. On the base is a plate engraved with the coordinate lines for a particular latitude. Over it sits an open-work fretted plate called the rete, cut away into curling points, and each point is the position of a named star. The rete rotates. Turn it, and you are turning the sky. On the back there is a sighting arm. Hang the instrument from your thumb, swing the arm until you have the sun or a star along it, and read off the altitude. With that measurement and the rotating rete, you can find the time of day or night, your latitude, when a given star will rise, the direction of Mecca, the times of prayer, and the height of a tower or the depth of a well. It is an analog computer. It solves a large class of problems by physically modeling the geometry of the situation, and it does it in something you can carry in a satchel. They were made to an extraordinary standard, engraved and inlaid, and hundreds survive in museums. Some of them are signed, and among the signatures is that of a woman, Aliglia, who made astrolabes in Aleppo in the 10th century. The observatories grew steadily larger. At Maragay in Persia in the 13th century, under Mongol patronage, a major institution was built with a large staff and a substantial library. And there, Nasir al-Din al-Tusi and his colleagues attacked the internal inconsistencies of Ptolemy's system. They devised new geometrical arrangements, one of which is known as the Tusi couple, which produces straight-line motion out of two circles. That device appears later in the work of Copernicus, in the same form, without attribution. Whether he arrived at it independently, or by some route of transmission through Byzantine or Italian sources, is still argued. And at Samarkand in the 15th century, a prince who was also a serious astronomer built the greatest observatory of the pre-telescopic world. Ulugh Beg was the grandson of Timur, and he was more interested in the sky than in ruling. His observatory contained a sextant of enormous size, a curved arc of stone set into a trench cut in a hillside, its radius around 40 meters, so that the scale could be graduated finely enough to measure angles to a few seconds. With it, he and his team produced a new star catalogue, compiled from fresh observation rather than copied from Ptolemy, containing over 1,000 stars. It was the most accurate in the world, and remained so until the work of Tycho Brahe, over a century later. He calculated the length of the sidereal year and got it wrong by less than a minute. He was murdered in 1449 on the orders of his own son, and the observatory was destroyed by religious opponents not long afterwards. The trench survived, buried, and was rediscovered by an archaeologist in 1908. The legacy that touches you most directly is in the names. Look up tonight, and the bright stars you can name in English are, most of them, speaking Arabic. Betelgeuse, Rigel, Aldebaran, Altair, Vega, Deneb, Fomalhaut, Algol. They came into Europe with the translated star catalogues in the 12th and 13th centuries, and they simply stayed, mangled by transcription through Latin, some of them almost unrecognizable now, but there. Aldebaran means the follower, because it comes up behind the Pleiades and appears to chase them across the sky. Somebody noticed that and named it for the noticing, and 1,000 years later we are all still using his word. In Europe, through the centuries when Baghdad and Samarkand were doing the serious work, the sky was mostly being watched by men in cold buildings at 3 in the morning. Monastic life ran on a timetable of prayer, 8 offices spread across the day and night, and the 2 hardest ones fell in the dark. Matins in the small hours, and lauds at first light, which produces an immediate practical problem. In a stone building, in winter, with no clock, how does anyone know when it is time? Somebody had to stay awake and watch the sky. There is an instrument for this called a nocturnal, and it is charmingly simple. A small disc with a handle, with a rotating arm and a hole in the center. Set the disc for the date. Look through the hole at Polaris. Swing the arm until it lines up with the 2 pointer stars of the plow, which turn round the pole like the hand of a clock. Read the time. That is a functioning clock made of wood or brass, using the rotation of the earth as its movement, in the hands of a monk standing in a cloister in the cold with his breath showing. The other great timekeeping task of the medieval church was harder, and it drove a surprising amount of European mathematics. The date of Easter. Easter is defined as the first Sunday after the first full moon, on or after the spring equinox, which means calculating it requires you to combine a lunar cycle, a solar event, and a 7-day week, none of which fit together. The discipline of working it out was called computus, and it was the most technically demanding thing most educated men in early medieval Europe ever did. Tables were compiled and circulated. Arguments about the correct method split churches. Bede, working in a monastery in Northumbria in the 8th century, wrote the standard treatise on it, and in the course of doing so, gave a clear explanation of tides being governed by the moon, based on observations along his own coast. The buildings themselves were oriented. Churches across Europe were laid out with the altar to the east, towards the sunrise, and in a fair number of cases, towards the sunrise on the feast day of the saint to whom the church was dedicated. Stand in the nave of an old parish church on the right morning, and the light comes down the length of it and lands where it was meant to. The great change came in the 12th century, through Spain. Toledo had been under Muslim rule for centuries and had libraries. When it passed into Christian hands, scholars began arriving from across Europe to translate what was in them, working with Arabic-speaking Jewish and Christian intermediaries. What came out of that was the whole inheritance. Ptolemy, Aristotle, Euclid, the Indian numerals, al-Batani's corrected tables, al-Sufi's star names, al-Khwarizmi, whose name became the word algorithm, and whose book on calculation gave us the word algebra. Europe got its astronomy back, improved, in a language its scholars could read, and the universities that were forming at Paris and Oxford and Bologna had something substantial to teach. A Castilian king, Alfonso X, commissioned a new set of planetary tables in the 13th century, compiled at Toledo by a mixed team of Christian, Jewish, and Muslim astronomers. The Alphonsine tables were the standard reference across Europe for 250 years. There is a remark attributed to Alfonso, probably apocryphal, that if the Almighty had consulted him before the creation, he could have suggested something simpler. It captures the mood of anyone who has ever tried to make the Ptolemaic system fit. Then the ships went out, and everything became urgent. Here is the problem that dominated the next 400 years of practical astronomy, and it is worth stating precisely, because it is one of the great unsolved problems of history, and its solution changed the world. Position on a globe requires 2 numbers: latitude, how far north or south; longitude, how far east or west. Latitude is easy, or at least soluble. Measure the height of the pole star above the horizon, and that is your latitude. Or measure the height of the sun at noon, and correct for the date using a table, and that gives you the same thing. The sky tells you directly, because latitude is a physical relationship between you and the axis of the Earth. The instruments improved steadily. The quadrant, a quarter circle with a plumb line. The cross staff, which you sighted along with a sliding crosspiece, and which required you to look directly at the sun, and blinded a great many navigators over the years. The backstaff, invented by an English captain who had gone half-blind himself, which let you take the sun's altitude with your back to it, using its shadow. Eventually the sextant, with mirrors, which brings the image of the sun down to the horizon so that both can be held in view at once, on a moving deck, and which is accurate to a fraction of a minute of arc. By the 18th century, a competent navigator could establish his latitude to within a mile or two. That is why the sailing routes of the age of sail look the way they do on a map. Ships would run north or south to the latitude of their destination, well out to sea, and then turn and sail along it until they hit something. It is the same technique the Norse used, refined with brass. Longitude was a different order of problem, and for a long time it looked insoluble. The Earth turns once in 24 hours, so longitude is really a question about time. If you know the time at some fixed reference place, and you can determine the local time where you are, the difference tells you your longitude. Every hour of difference is 15 degrees. Local time is straightforward. Wait for the sun to reach its highest point. That is local noon. The reference time is the difficulty. You need to know, out in the middle of the ocean, what o'clock it is in London, which requires either a clock that keeps accurate time on a rolling, damp, temperature-swinging ship for months, which did not exist, or an astronomical event visible from everywhere at the same instant that could serve as a signal. Both approaches were tried for centuries. Both eventually worked. The Portuguese ran into the associated problems first, going down the coast of Africa in the 15th century, because as they crossed the equator, the pole star sank below the horizon and vanished. There is no southern pole star. There is nothing bright at the south celestial pole at all. So they learned to use the sun's altitude at noon instead, with tables of declination prepared by astronomers back home, and they learned to use the Southern Cross, that small bright constellation which points towards the pole without occupying it. Columbus, in 1492, was navigating essentially by dead reckoning and instinct. He estimated his longitude, and he was consistently, catastrophically wrong, which is one of several reasons he was convinced he had reached Asia. He did once use astronomy to considerable effect, and the story is well documented. On his fourth voyage, in 1504, he was stranded on Jamaica with worm-eaten ships and a crew he could not control, and the local people, having initially supplied him, had stopped. He had with him an almanac by a German astronomer which predicted a total lunar eclipse for the 29th of February. He requested a meeting with the local leaders and told them that his god was angry at the withholding of provisions and would demonstrate this by taking away the moon. The moon duly went dark and turned red. Provisions were supplied. Columbus retired to his cabin with an hourglass, waited until the eclipse was nearly over, and emerged to announce that his god had been placated. It is a squalid story, but it is a perfect illustration of what astronomical knowledge was worth in that period, which is to say, power over people who did not have it. Magellan's expedition, which left in 1519 with 5 ships and returned 3 years later with 1, produced the first proof of the Earth's circumference by circumnavigation, and also a small mystery that turned out to be profound. They kept a careful log. When the survivors reached the Cape Verde Islands, they found that their date was 1 day behind everyone else's. Nobody had lost count. Sailing steadily west, they had gained a day, because they had gone right round the world against the direction of its rotation, and experienced 1 fewer sunrise than the people who stayed behind. It caused genuine consternation, because it had consequences for the church calendar. It is the reason there is now an international dateline. By 1714, the longitude problem had become so serious and so expensive in wrecked ships and lost cargoes and drowned crews that the British Parliament passed an act offering a prize of £20,000, an enormous sum, for a practical solution. Most of the scientific establishment expected the answer to be astronomical. The favored approach was the lunar distance method, using the moon's position against the background stars as a clock face, which works, but requires precise tables, a good instrument, clear skies, and about 4 hours of laborious calculation for each fix. The prize was substantially won by a Yorkshire carpenter with no formal education. John Harrison spent more than 30 years building clocks. His early sea clocks were large brass machines with counterbalanced oscillating bars, linked by springs, so that the motion of the ship affected both equally and cancelled out, and with a bimetallic strip to compensate for the way temperature changes the length of metal. Then, having built 3 of these, he did something unexpected and abandoned the whole approach in favor of a large watch. H4 is about 13 centimeters across and looks like an oversized pocket watch. On a voyage to Jamaica in 1761, it lost about 5 seconds in 81 days. That is an error of longitude of roughly a mile. The Board of Longitude, whose leading members had a professional and personal preference for the astronomical method, made him prove it repeatedly and disassemble it and hand it over, and paid him in stages over years, and he received the balance only after an appeal to the king when he was almost 80. Both methods went to sea together in the end. The chronometer for the daily fix, the lunar distances as a check when the chronometer's reliability was in doubt. Which brings us to James Cook, who was probably the finest practical navigator of the age, and whose first great voyage was, in origin, an astronomical expedition. In 1769, Venus was due to pass directly across the face of the Sun. These transits come in pairs, 8 years apart, and then not again for over a century. Their importance was this: if the transit could be timed accurately from widely separated points on the Earth, the differences in timing would allow the distance from the Earth to the Sun to be calculated by triangulation. That number was the fundamental yardstick of the solar system. Relative distances between the planets were well known. The absolute scale was not. Get the distance to the Sun, and everything else follows. So expeditions were sent all over the world, and Cook was sent to Tahiti, and the observations were made, and they were less precise than hoped because of an optical effect at the edge of the planet's disk that made the exact moment of contact difficult to judge. The eventual result was still the best measurement of the size of the solar system anyone had, and it was obtained by an international scientific collaboration of a kind that had not really existed before, involving nations that were at war with each other during the period, which is a rather good thing to have happened. After Tahiti, Cook opened his sealed orders and went south to look for a continent, and mapped New Zealand and the east coast of Australia with an accuracy that stands up against satellite data today. On his second voyage, he carried a copy of Harrison's watch, and he wrote about it as a faithful guide through all the vicissitudes of climates. Picture that ship, middle of the Southern Ocean, cold spray, canvas hard as board, and the officer of the watch with a sextant to his eye, bracing against the roll, bringing the reflected image of a star down to touch the black line where sea meets sky, and calling the moment. Below, in a padded box in a locked cabinet, a watch is quietly keeping London time to within a few seconds a month. Between the two of them, on a wooden ship in the middle of nowhere, a man could now write down where he was, and be right, and someone else could sail there and find the same place. A canon of the cathedral at Frombork, on the cold Baltic coast of what is now Poland, spent 30 years not publishing a book. Nicolaus Copernicus was an administrator, a physician, an economist of some ability, and an astronomer in his own time. He worked in a tower attached to the cathedral wall, and the Baltic weather being what it is, his opportunities for observation were limited, and he made rather few of them. What he had instead was an aesthetic objection. The Ptolemaic system worked, more or less, but by the 16th century, keeping it working required a great deal of machinery. Epicycles on epicycles, offset centers, and a particularly awkward device called the equant, which allowed a body to move uniformly around a point that was not the center of its own circle, which contradicted the whole principle the system was supposed to embody. It had become, in his view, a monster, accurate in parts and incoherent as a whole. So he tried the other arrangement: put the sun at the center, let the Earth be a planet, third out, turning daily on its axis and traveling annually round the sun. And several ugly things immediately became simple. The backwards loops of the planets, which had required all those epicycles, fall out automatically. When the Earth on its faster inner orbit overtakes Mars, Mars appears to move backwards against the stars, in exactly the way a car you are passing appears to slide backwards against the landscape. No mechanism required. It is a consequence of the viewpoint. The order of the planets, which in the old system was arbitrary, becomes fixed. The further out, the slower, in a clean progression. Copernicus was not entirely right, and it is important to say so. He kept perfect circles, because he was as committed to them as Plato had been, and consequently his system needed epicycles of its own, and was no more accurate than Ptolemy's. Its virtue was elegance, not precision. He circulated a summary among friends. He delayed the full book for decades, partly from fear of ridicule rather than of the Church, which at that stage had no settled view. The book was published in 1543, and the story is that a copy was placed in his hands on the day he died. Then, a Danish nobleman with a metal nose gave the world the data. Tycho Brahe lost part of his nose in a duel over a mathematical dispute and wore a prosthetic for the rest of his life. He was arrogant, extravagant, and one of the great observers in history. The Danish king gave him an island, and on it he built Uraniborg, a combined house, laboratory, and observatory, and then a second sunken observatory nearby, to shelter his instruments from the wind. He had no telescope, nobody did. What he had was instruments of unprecedented size and construction, built to his own designs, with scales he could read finely, and a rigorous program of repeated measurement over 20 years. He pushed naked-eye astronomy to its physical limit, achieving accuracy of around 1 or 2 minutes of arc, which is roughly the resolution of the human eye. And he found things that should not have been there. In 1572, a new star appeared in Cassiopeia, bright enough to be seen in daylight. Tycho measured it repeatedly and could detect no parallax, which meant it was not close. It was out among the fixed stars, in the region that was supposed to be eternal and unchanging. It was a supernova. In 1577, a great comet appeared, and again he measured, and again there was no parallax, which put it well beyond the moon and moving through the region where Aristotle's crystalline spheres were supposed to be. If the comet passed through them, they could not exist. Tycho himself never accepted a moving Earth, and proposed a compromise in which the planets circle the Sun, while the Sun circles a stationary Earth. It fits the observations available to him perfectly well, which is worth remembering. He died in Prague in 1601, and his observations passed to his assistant, who was everything Tycho was not. Johannes Kepler was poor, sickly, socially awkward, a brilliant mathematician, and a mystic. He believed the universe was built on geometric harmony, and he spent years trying to fit the planetary orbits inside a nested arrangement of the 5 regular solids. He was given the Mars data. Mars has the most eccentric orbit of the planets easily observed, which is why it had always been the worst behaved, and Kepler spent something like 6 years on it. Thousands of pages of calculation, done by hand, with no logarithms for most of it. He got a circular model that fitted Tycho's observations to within 8 minutes of arc. 8 minutes is a very small quantity. It is a quarter of the width of the full moon. Almost any astronomer before Tycho would have declared victory, because no earlier data was good enough to detect the discrepancy. Kepler knew Tycho's data was better than 8 minutes. So the model was wrong. He threw away years of work over a discrepancy most people would not have been able to measure. And that decision is one of the finest things anyone has ever done in the name of getting it right. He tried other shapes. Eventually he tried the ellipse. It fitted. The planets move in ellipses with the sun at one focus. They sweep out equal areas in equal times, which means they move faster when nearer the sun. And the square of the orbital period is proportional to the cube of the average distance, a relationship that ties the whole system together in a single line of arithmetic. 2,000 years of perfect circles ended there, in the notebooks of a man who had been trying to prove something else entirely. Meanwhile, in Italy, in the autumn of 1609, a professor of mathematics at Padua heard that a Dutch spectacle maker had produced a device that made distant things look nearer. Galileo Galilei never saw the Dutch instrument. He worked out the principle, ground his own lenses, and within months had built one far better than the original, magnifying about 20 times. He sold the idea to the Venetian Senate as a naval instrument, which it certainly was. Then he turned it upwards, which almost nobody had thought to do, and the sky came apart. The moon was not a smooth celestial sphere. It had mountains. He could see the shadows they cast, and watched the shadows shorten as the sun rose over them. And he measured the heights of lunar mountains from the geometry of their shadows, and got sensible answers. The Milky Way was not a cloud. Turn the instrument on it, and it dissolves into stars, thousands of them, more than could be counted. Venus went through phases like the moon, from crescent to full, which is impossible in the Ptolemaic arrangement, and exactly what you expect if it circles the sun. And then the 7th of January, 1610, he pointed the telescope at Jupiter, which was well placed that winter. Beside it he saw 3 small stars in a line, 2 on the east, 1 on the west. He noted them and thought little of it. The next night he looked again, and all 3 were on the west side. That should not happen. Jupiter should have moved against the background stars, not the other way, and it should not have moved in that direction. He watched again on the 11th. 2 stars, east. On the 12th, 3 again, 1 very faint. On the 13th, 4. 4 small points of light, in a line, changing position night after night, always strung along the same axis, never straying from it, some of them occasionally vanishing behind the planet and reappearing on the other side. They were going round Jupiter. Sit with that for a moment on that cold January night, at a window in Padua, with a homemade tube of leather and glass. The central claim of the geocentric system was that everything circles the Earth. It was not merely an astronomical position. It was the architecture of the universe as understood by essentially everyone in Europe. And here were 4 objects, visibly, incontrovertibly, going round something else. He published within weeks, in a short book called The Starry Messenger, and it made him famous across Europe within months. What followed took 23 years and ended badly. His advocacy for the Copernican system, his talent for making enemies, his decision to put the Pope's argument into the mouth of a character named Simplicio, and the political pressures of the Counter-Reformation combined into a trial before the Inquisition in 1633. He was made to abjure, and he did, and he lived out his last years under house arrest in a villa outside Florence, going blind, dictating to a student the book that laid the foundations of the physics of motion, because he was forbidden to publish and had it smuggled out and printed abroad. The story that he muttered a defiant phrase about the earth moving as he rose from his knees is almost certainly a later invention. The last piece arrived from a farmhouse in Lincolnshire. When plague closed Cambridge in 1665, a student in his 20s went home to Woolsthorpe and spent the best part of 2 years thinking, and in that time laid the groundwork for calculus, for the theory of color, and for gravitation. Isaac Newton's question was not why things fall, it was why the moon does not, and his answer was that it is falling, continuously, and missing, because it also has sideways motion. A body moving fast enough horizontally will fall towards the Earth at exactly the rate the Earth curves away beneath it, and will therefore go round and round forever. The same force that pulls an apple down holds the Moon in orbit. The same force keeps the planets on their paths around the Sun. He worked out its form. Every mass attracts every other mass, with a strength proportional to the masses, and falling off as the square of the distance between them. That is one sentence, and out of it, Kepler's 3 laws drop as mathematical consequences: the ellipses, the equal areas, the relationship between period and distance. Kepler had found them in the data without knowing why they were true. Newton showed why they had to be. The Principia was published in 1687 at the expense of his friend Edmond Halley, who also used the new theory to calculate the orbit of a comet, predicted its return in 1758, and did not live to see it come back exactly as he had said. Consider what had happened across those 150 years. The heavens and the earth had been 2 different kinds of place, made of different material, obeying different rules, since Aristotle. The sky was perfect, and the world was corrupt, and there was a boundary at the moon. Newton removed the boundary. 1 set of laws, same rules everywhere. The stone in your hand, and the moon over your head, and the most distant planet, all doing the same thing for the same reason. The sky stopped being a different country. And with that, the language everyone had been trying to read for 5,000 years turned out not to be a message at all. It was mechanics, beautiful, exact, and indifferent. So the mystery was solved, and something was lost in the solving, and it is worth being honest about both halves. What was gained is not in question. We know what the stars are. They are suns, some of them vastly larger than ours, burning hydrogen into helium under their own crushing weight. And when they exhaust it, the large ones collapse and detonate. We know how far away they are, which is further than any ancient astronomer would have found tolerable. The nearest is 4 light-years off, and the light entering your eye from it tonight left before you had heard of it. We know the Milky Way is a galaxy of a few 100 billion stars, seen from the inside, from a position about 2/3 of the way out, along one of its arms, which is why it looks like a band across the sky, rather than a spiral. We know there are perhaps 2 trillion other galaxies, and we know something that would have startled every single person in this story, which is that the material we are made of was manufactured inside stars. The calcium in your bones, the iron in your blood, the oxygen you are breathing at this moment. None of it existed at the beginning. All of it was assembled in stellar cores and scattered by explosions, like the one the Chinese astronomers wrote down in 1054. Every culture in this story believed there was a connection between human beings and the lights in the sky. Every one of them. They were right. They were entirely wrong about the mechanism and completely right about the fact. What was lost is harder to name, but you know it if you have ever been somewhere genuinely dark. The sky stopped speaking. For 5,000 years, looking up meant reading a message addressed to you. Your ancestors were there. Your gods were there. The order of the heavens told you when to plant and when to sail, and how the world was arranged, and what would happen to you after you died. Now it is mechanism, beautiful and comprehensible, and not addressed to anybody. And yet, go somewhere without lights. A moor, a desert, the middle of an ocean, a mountain. Wait for your eyes to adapt, which takes a full 20 minutes, and which almost nobody has the patience for, and then look up at a properly dark sky. Nobody is unmoved. Not scientists, not skeptics, not people who know precisely what they are looking at. The reaction is completely reliable, and it does not depend on belief. Something in us still responds to it exactly as it always did, which is worth sitting with, because it suggests that the response was never really about the explanation. The explanation was the thing people built afterwards, to have something to say. The looking came first. We have made it much harder to do. Artificial light now spills upward from every populated region of the Earth, and it scatters in the atmosphere and produces a glow that drowns the stars. The Milky Way, which every human generation before about 1950 could see as an ordinary feature of the night, is now invisible to something like 80% of people in Europe and North America. There are children in cities who have never seen more than a handful of stars. Not because of cloud, because the sky where they live is not dark anymore. There is a well-documented incident from Los Angeles during a power cut in the 1990s, in which people rang emergency services to report a strange silvery cloud overhead. It was the galaxy. They had simply never seen it. That is a loss of a particular kind, not of knowledge, because the knowledge is written down and safe, of contact, the direct experience that every one of your ancestors had, every clear night of their lives, and that you may have to travel a long way to obtain. So why do we still look up? Not for navigation. There is a satellite doing that, more accurately than Mao Piailug could, and nobody is going back. Not for the calendar. Your phone knows the date. Not for omens, unless you want them, and no eclipse now threatens any king. We look up because of something older than all the uses, which is the reason the uses were found in the first place. It is the only direction in which there is no wall. Everywhere else, the world stops. Rooms have ceilings, valleys have ridges, the sea has a horizon, and every one of them is a boundary at a knowable distance. Look up and there is nothing between you and everything, all the way out, for as far as it goes. And it is the only view that has not changed. That is the thing worth taking to sleep with you tonight. Everything else in this story has gone. The wool workers' fire on the plain, the mud brick cities that became hills, the temple on the roof of which a priest waited 19 mornings for one star, the library at Alexandria, the bronze machine on the sea floor, the tower at Samarkand, buried in a hillside, the city on the lake, drained and built over, the forest that took back the round tower and the spiral stair. The languages are dead, the gods are unworshipped, the names of nearly everyone involved are gone, and the few that survive are the merest fraction, and even those are mostly just names. But the sky those people were looking at is the sky above your roof tonight. Precisely, not approximately. The pattern of Orion that an Egyptian called Sahu and hung his hopes of eternity on has not measurably altered. The Pleiades that the Aztec priests watched cross the meridian are crossing it still, on schedule, tonight, whether anyone is on the hill or not. The star that Sirius announced the flood with rises in the same place. Aldebaran is still following the cluster it was named for. You can walk outside tonight and see, with your own eyes, the identical arrangement of light that a Babylonian scribe pressed into wet clay, that a Polynesian navigator steered by, that a Norse helmsman searched the cloud for, that Galileo turned his tube towards. There is nothing else in the human world of which that is true. No building, no language, no border, no book. It is the one thing we have all had in common, the whole way through. So let the day go now. Let your breathing slow. It has probably already started to. Let your shoulders come down and stay down, and your jaw unclench, and your hands open. Let the mattress take the whole weight of you, because it will, without any help. Let the names go. They were never the point. Sirius, Sahu, the Nakshatras, the Saros, the star houses on the horizon. None of it needs to be carried anywhere. You are lying in the dark, and above the roof, above the cloud if there is cloud tonight, above the glow of whatever town you are near, the whole enormous silent structure is turning, slowly, in the same direction it has always turned, at the same rate. Fires went out, cities fell into their own dust, ships went down and were forgotten. Books were burned in a square in the Yucatan and in a library on the Egyptian coast. and what was in them is gone and is not coming back. Long after the empires crumbled, long after the kings and the queens were forgotten, the stars remained exactly where they had always been, silent, patient, waiting for the next generation to look up. Thank you for spending these hours with me. Whatever time it is where you are, whatever kind of day it was, it is finished now. Rest well. Sleep into power, guys. Good night.